Um, all right, I think, yeah, everyone enjoy lunch? I think you did. You definitely enjoyed the desserts because there weren't any left. Thanks a lot. So registration, by the way, closes at 3:30. So if you're watching on the live stream, for some reason you haven't registered yet, I don't know why, you should definitely do that. Otherwise, we will not let you in to the reception later. Yeah. Well, you probably will anyways, but you should register. I'm pressing this. There we go. Okay, so our next speaker is Steve McGuire. Last year at ReactConf, Netflix celebrity developer Jafar Hussain spoke about Gibbon. So Gibbon is Netflix's React renderer that is optimized for your television. On Twitter, after his talk, he attributed Gibbon's success to developer extraordinaire Steve McGuire. So ladies and gentlemen, Steve McGuire.
Hi, I'm Steve. I work on the UI platform team at Netflix. And one of the things I think is really cool about conferences like this is it's clear that we're all kind of co-discovering better ways of doing things right now, or maybe just rediscovering. And one of the challenges that comes with that is we'll often hit setbacks when we try to apply these concepts. And with those setbacks comes the temptation to compromise on our architectures, and often in the name of performance. So what I want to talk to you about is how we were able to deliver a performant UI without compromising on any of our ideals, and most of them overlap with what's been covered here. So a while back, we set out to rewrite our existing UI that dates back all the way to 2009 and was showing the scars from years of A/B testing, a few UI implementations on top of it across various devices, and even a switch to a totally new rendering engine that was just mentioned, it's Gibbon, away from WebKit. And we knew that we wanted to use React because it allows us to treat the UI as almost a pure function of state into DOM. But that purity comes with a cost, and we run on a very wide array of devices, so this was a bit of a challenge. And so, for example, we run on PS4s or smart TVs or very low-powered devices like streaming sticks. And speaking of those streaming sticks, the one that we target, which is roughly $30, is armed with a 600 megahertz single-core processor, an absolutely tiny L1 cache, is running a custom-built JavaScript core with no just-in-time compiler, and altogether it ends up being about 465 times slower than V8 running on a typical developer laptop. But one of the early optimizations or innovations that we made, and this was even before we were using React about 3 years ago, was Gibbon. So one nice thing, something about this is that it was just a custom rendering framework. We wanted to throw out a lot of the overhead from WebKit, like CSS, HTML, and just have these primitive boxes. So we just drop images or text or whatever we want inside of them. And so you end up with this asynchronous JS context into a 60 frames per second render loop. So we don't ever end up blocking animation for executing JavaScript. And so we were ending up with this, in early experiments, a Gibbon-specific React fork that was kind of using a DOM wrapper, but then React Native was released just in time as we were about to exit that experiment, and we were able to just base React Gibbon on React Native, and they also follow a very similar architecture in terms of a bridge hop to push properties across. And another nice thing about this is, as we wanted to move more towards production, we were able to use React Gibbon as a place for focus management or declarative animation or layout. But as the title of the talk stresses, we wanted to be both pure and fast. And so to cover some of the architectural principles that we wanted to follow, as has also been covered by a few speakers here, unidirectional flow was very important to us. Also composition over inheritance and having always declarative APIs. We never call downward through a component tree to drive effects. So just to revisit unidirectional flow real quick, this is what our existing application might look like, where we have this observation hell where various components will have this global dispatcher that they can publish keyed events on, subscribe over here somewhere else, and there's really no sense of ownership about effects anymore. There's no ownership of anything, really. And it just causes a lot of bugs. It makes the entire system harder to maintain. And so, speaking to that, I already covered kind of the idea that various components can just kind of hop over to each other. There's no downward flow of information. And because of that, as various asynchronous actions resolved, you ended up with a lot of race conditions, and they were often not even caught until we hit production. So following the Flux model makes it a bit better in that it's at least encouraging this closed loop where you go top-down with every action. But that was a lot of boilerplate versus something like Relay, particularly in a read-only case where we're not using something like mutations. We just want to go and query some data and drive it into some views because it's a very content-driven, consumer-based application. And so by unidirectional flow, again, I mean this kind of action to state to DOM back around. I think we're all familiar with that. And we ended up not using Redux or anything like that because it actually didn't exist when we set out on this project. So we have this very lightweight state component that we use. And so if I go and touch something fairly far down, it's going to dirty that node, as well as every parent up to the root. And then we'll just turn around and do a top-down render, just touching the views, let's say, that whose state was different as it was feeding in. So going over composition over inheritance, that really meant no mixins. And as you can see, just by looking at this, mixins have issues where you can't even really tell, unless you really squint at this, where one ends and the next begins. And we really preferred high-order components, where the output of one feeds into the input of the next. And I don't know if I'd say there's clean separation, but there's separation. So illustrating mixins. So let's say we have this plain video component that's just a dumb render of props. And we want to blend focus management into this. So right here, it's not so bad. You might have some implicit hooks between focus where you can call things from video, or in turn, video is expected to satisfy the interface of focus. And if I had another behavior, like some data management, again, this could be Relay, it could be Falcor or anything, then it's the same story. It's not that bad necessarily, but often there's a blended concern between the application state and the data management, and you'll start to see that you clash in terms of namespacing of your state, of your APIs, and also as I refactor this over time, I might leave behind APIs that I don't even realize were satisfying one or the other anymore. Where with high-order components, it makes a lot more sense that things just kind of flow from the outside in, and I can just stack more and more of these transparently. But also, we were refactoring heavily as we experimented with this UI, so as we go into the future as well, right now we might be using Falcor, but maybe we end up really liking Relay better, or Redux, or whatever comes after it. Or maybe we're unit testing and we just want to have static data feeding into this. Or maybe also, due to a refactor, we just have various aspects of our UI's data concerns satisfied by multiple of these, and they can just stack up. And just to illustrate with code what mixins end up looking like, so I have no idea who getPath or getFields is for. It's totally unclear, and it's not like I have syntax highlighting that shows me which of these mixins are being satisfied. But with high-order components, it's much more clear. I've got some config that's going to travel with this composed component, and list feeds into data, or rather, it's kind of the opposite. State feeds into data, data feeds into list. And there's just a clear ownership chain there. And so just to also cover one of the issues with mixins is as you kind of want to propagate information through the stack, trying to send something from state to data as a mix-in becomes very difficult. There is a way to do it, and I don't even know how many people are even familiar with this API, where you can give a function to set state. It'll give you the existing state on that component's namespace, but now you're going to have to use implicit shared key in order to get information between these two. So one other thing that we wanted to emphasize was being always declarative. And that's very challenging because versus most applications, we don't really have a lot of pointer input. We do have to support that, but usually as we're walking through various UI elements, we have to walk it via just key presses. And so the problem with refs, though, which is how people tend to drive focus, there's really no sense of ownership again. You can have n number of owners all driving effects into your application or your component, where if you always just go via render and props, there's again just kind of a one-to-one relationship there. So I just want to illustrate what focus might look like with refs, where we get a key press and we want to go from the element 0 to element 1 as being the selected item. So it works out so far. I just go ahead and call items 1 focus, and internally it just says, hey, image.focus. But what happens when I add another component around that transparently? And it could be a higher order component, it could be something more meaningful. I've just broken the interface of this thing, and so I'm going to have to go through the trouble of actually manually propagating that interface through, or find some other way to do this. But also, if this is conditionally rendered, I'm going to have to do a bunch of null checking to see if these things are even on screen yet and if I can focus them. And so you can manage all this, but it ends up becoming a bit of a mess versus just returning an element from render. So we ended up with a declarative focus system supported by React Gibbon. So in this case, we would just do a set state with a focus ID. We would return that item with focus true, and in turn, it would tell the actual React Gibbon image that it's focused. And in turn, if I go ahead and make some kind of wrapper around this item, it still just kind of works itself out because the props are going to end up where they're supposed to be. And again, if it's asynchronously resolved, it's not that bad because even if we were, for some reason, setting state to the next list item, which perhaps I wouldn't do, by the time everything comes back, they're all going to get the right props. So we ended up with a somewhat dogmatic rule that we would never, ever use refs. And so far, we've not had a realistic case where we had to bail on that. But again, we wanted to be pure and fast, and taking away these kinds of escape hatches really makes that challenging. So to outline what fast means to us, though, so for key responsiveness, again, we're using just left, right, up, down typically. Most people can start to notice a lag once you get beyond 100 milliseconds for getting an action from the user onto the screen. And it's made even worse by the fact that a lot of newer displays will add upwards of 30 milliseconds of latency. And in terms of animations, just about everybody can notice if things drop below 60 frames per second. That's generally the bar. It's been fairly easy to hit with Gibbon, and it's not really exacerbated by React. That's more about JS time. So again, this is very ambitious for a device that's 465 times slower than your laptop. And so this device I'm speaking to, we were really iterating on the absolute slowest we could find on the very hardest screen we could create, which you see right here. So in this screen, there's roughly 150 elements at any given point. That's just plain primitives, not including all of the data components or state components or focus components that might be supporting this. And it was important that we not get bogged down optimizing the entire way because we might throw out some part of the architecture anyway, but we did want to measure every step so that we knew where to go back and clean up. And so with measuring, we found out we were off by our target by almost double. And so we examined higher order components, which are fantastic as an abstraction, but they were very expensive for us. In fact, on this particular device, the complete lifecycle for one of those components is about 1.2 milliseconds, and that's just a plain no-op pass-through. And in this scene, we've got 6 high-order components per list, and there's about, let me see, 6 of them that are invisible to you right now because we have to animate them in, but there's 8 lists here, plus all the ancestors because we're doing a top-down render. That added up to about 60 milliseconds of mandatory overhead that we weren't even getting any benefit from. So what were we to do? Should we go back to Nixon's? And our answer was absolutely not. So again, to revisit higher order components, they're really isomorphic to higher order functions. Really, most of the time all they're doing is a reduce and a map and maybe giving some child context. And just to illustrate exactly what the relationship is here, component where we see props is really just a reduce, where we take the incoming props context in the previous state, and we might emit another state via set state. And in turn, transducers, they still need some way of saying, hey, I've got something for you, because they might be asynchronous. And in this case, for our API, it just ended up being on next. And render is isomorphic to map. So all you're doing is taking what was produced by a parent plus the internal state reducer and giving props to the next transducer or component in the chain. And then, of course, there's this, which has no corresponding concept because these are just stateless pipes. They don't really even have an instance. And just to put that into a drawing, of course, I think this ought to be familiar to some of you. Reduce just goes ahead and calls next, and then feeds into map, which is, again, like component where we see props, set state, render. But the cool thing about these is you can just kind of stack them up transparently, and from the outside, you'll just be able to call, hey, give me a new state. And if any of you are familiar with RX, they might also look like observables, just really lightweight. They don't have a lot of the bookkeeping overhead. And just to put this into code, for the minimum viable implementation that will mostly satisfy replacing a higher order component, so you want to pull off a namespace for this thing because you want to avoid the namespace clashes that you'd get with mixins. But then I want to get next state, get next props. So those correspond to reduce and map. And then I might invoke get next state, pull the state out of its namespace, send in the props and context, and give it a callback so that when I receive the state, possibly synchronously, possibly asynchronously, I can go ahead and merge that into the existing props, also merge it back into the state, because of course we need to be immutable here, since things might resume and keep calling forward. And then, since we're really walking through a linked list of transducers, or maybe components, we want to check to see if there's another one to invoke. Otherwise, we're done. Let's go ahead and emit the final props and state to whoever invoked us. It might just be a wrapper around transducers. So these transducers mitigated a lot of the component overhead for us, but they're not perfect. We definitely followed the philosophy of moving fast and breaking things. So lacking this might be a good thing, it might be a bad thing, depending on your philosophy. But the merges are still costing a lot of time. That's, in fact, the slowest thing that we can do on our platform. And in looking deeper, rather than creating this whole new concept, maybe we should have just written a different, more specialized React composite component, and that might be where we end up taking this. But we did get some wins out of this performance-wise, and it cut off about 50 milliseconds. So taking away refs, though, and forcing this always declarative, always top-down render came with costs via forcing us to always reconcile children, styles, et cetera. And we were doing a lot more of it now, where before we could just bypass a lot of the component tree. So what were we to do? Could we return to refs? And again, absolutely not. So one really basic thing that we were able to do that was very easy and we did early on was to separate our styles into static and dynamic. And so, for example, if I have 4 properties here that are very well known. They're just literals. And one that's dynamic, what it would look like here in the default React diff is I have to look at the previous styles, loop over them. If they're not in the next style bag, I need to wipe them out against the actual DOM node, and then loop through the next styles and apply them. So that's very costly, again, because those for in loops and the dynamic key lookups are very slow for us. So it's very easy then to just break out the things that we know are going to be dynamically diffed, and just always skip the things that we know aren't going to change. And so how that looks in code is just, hey, I've got a static style key. And another reason to do this, though, as opposed to folding it into what I'm going to show you next, we might change these static styles at runtime based on locale changes or profile changes. And so one step further that we took is to create an actual Babel transform that writes a static diff for us. And so again, looking at a very simple video component, what you're able to do, just by looking at the style that we emitted, you can actually see that the only thing that might change is rect. So why not just write a function that's very specialized and pass it along on the element? And so before we were doing this dynamic for in loop, and again, it just goes to a simple one key check to one key check, apply if it changed. But we have to give up on this in certain scenarios, and we could probably try harder and chase down some of these scenarios that cause us to de-optimize, but the transform would get slower, it would get more complex, and instead we just warn developers when they cause a de-opt. But for example, mutating this bag makes it impossible to, or unsafe to write that static diff function. Also, aliasing might result in mutation of the alias, so again, we give up and warn. Also, calling and sending this to a function is going to be an implicit alias, and receiving it from a dynamic path that is somebody else passed it into us, we don't know where it came from, therefore we don't know its structure. But the cool thing about JSX, whether you like it or not, is that it's a very useful compiler hint. It kind of lets us know that a diff is about to happen, so maybe we can apply some smarts to it. And some future work. This is, again, very crude. We just barely looked at this. But it would be cool to actually do static diffing of children, because that's also an enormous amount of overhead. It has to do the same thing, where it loops over the previous and the next. Flow also, it gives you information about the call graph of your modules, so you can actually just possibly fold that into Babel or make Babel do this as well, and not have to de-op in some of those scenarios. Also, for cases where there's not really a component relationship, like the transducers I was showing you, and I had to do these merges, maybe I can use JSX to say, write a fast merge function inline there, or even I've seen the Facebook folks have a GitHub issue open where they want to sort of tag elements so that they can memorize a diff function at runtime. And this is just an example of how we might do that. And so after these static optimizations, that cut off about another 40 milliseconds, and we were getting pretty close. But one thing we were able to just fold in that we didn't even have to create was the Babel element inliner, and you really should check this out if you're struggling with performance. Because, especially for us on our platform, maybe not for anybody running on a JITted VM, create element is very expensive, partly because even constructors are very slow for us versus just object literals. And internally, create element, even in production mode, has to do a prop copy. So, just to go back and forth, if you've not seen the inliner, it roughly turns what you see there into this. So it adds a bit more information that isn't really necessary to see here. But it just turns this enormous call into a simple object literal, which is always very fast. And in a lot of VMs, you're going to end up with like hidden classes and other optimizations. But this too has to de-opt under certain conditions. So for example, if I use refs, there's an issue where if I use a ref, now when I go to create the element, I have to know what the current owner of this thing is. So now I have to fall back to the react.createElement, which is going to be the slow path. That got us down to 90 milliseconds. And just to cover a couple other things that didn't really necessarily move the needle directly, but we took the time to perform. So for the transducers as well, because we had this known composed linked list of things to call through, we could make static copy functions. We know the structure of this thing, so we can use the ES6 template string syntax to write functions at runtime. And in almost every VM I've measured, it's as fast to invoke these as it is something that was parsed as just a JS file. Also, since we control all paths into our application via given, we know when we get an on key or a timeout or a load, so we were able to just write a very specialized React batching strategy that mandates that all state changes happen in a single tick, so we wouldn't end up with accidentally serial state updates, which was much slower. And so again, we succeeded at being pure and fast. We didn't have to compromise on our ideals that we set out with. And some of this, again, is fairly new. It's not yet open source, I have to admit, but now that we've kind of explored it, we'd like to start sharing it back and start a conversation with the community. That's it.
All right. Our next speaker is Cyrus Akbary. So Cyrus is here to talk to us about graphene. I hadn't heard about graphene before, so I looked it up on Wikipedia, and I'm just going to summarize it for you. So some consider graphene to be the most remarkable substance ever discovered. It's about 100 times stronger than the strongest steel. It conducts heat and electricity very efficiently and is nearly transparent. So obviously, graphene is an allotrope of carbon in the form of a two-dimensional atomic scale honeycomb lattice in which one atom forms each vertex. But everyone knows that part already. But how can this occur in a member of the flat polycyclic aromatic hydrocarbon family? So Cyrus Akbary can hopefully answer this for us and make all of our apps better in the process. Thanks.
Hello, everyone. I'm Cyrus Akbary, and today we'll be talking about a GraphQL framework in non-JavaScript servers. But before I even start, I would like to say hello to my mom. She's watching me from live streaming in Spain. So if you want to join me and give her a big applause. Yeah, Mom, thank you. Thank you, everyone. So mostly all the talks that we've seen today are about React and React Native. My talk is going to be a little bit different. I'm going to get a little bit deeper into backend because, oops, sorry, I didn't take this. Because backend, frontend, and backend are very related to each other. You cannot isolate backend without frontend. Like frontend, we really need data to render things, right? So how we can manage some kind of thing where everyone developing in frontend and backend are happy to work with. So I want to start telling you my love story with GraphQL and how I started believing that GraphQL is the next big thing. So let's put some context. I was working in a Django application. Django, if you don't know, is a web framework for Python that lets you construct very easily models in backend. But not only that, it also permits you to create front-end views very easily. So we were having our front-end views made by Django templates and some JavaScript vanilla code. However, for a front-end developer, they have to set up a wall server. That means also with the database for just modify, for example, a template. And we thought maybe that's not the best structure that we should have. So we migrate all the code to a React single-page application, and it worked very well. However, what about SEO? All the renders were happening in client-side, and we want to have some kind of server-side rendering that actually use our React front-end code. So how we can manage that with our current backend code, which was in Python. So we went to the most obvious idea. Just embed the V8 engine inside our backend. It's not that great? Yeah. You can make JavaScript work very easily in your backend. So after talking across all teams, because in my company, we were not only using Python. We were having Ruby on Rails stack, also Java, also PHP. So the V8 engine could be embedded anywhere. In Java, probably it's not V8, it's Nashorn, but you can make it work. So after talking across all teams, we decided that that was a good idea. That's the path we want to go. So this is how the example look like when we first approach this problem. We just have an index view in our Django component, in our Django application, and we rendered whatever component we want, passing some props. So imagine we are Family Guy fans, and we want to render the Peter Griffin page. So we have name Peter Griffin, and we have the company Peter Griffin Fox, I guess. So we want to render that, but what happens when we want to add more data into the template? For example, we want to add some friends into my template. So the development process looks like we have to go to the component, we have to change the layout in the component for appending this new data, and then we have to go back to the server to append again the data. Because if not, nothing will show. So at one moment, one question arises. Why does the server have to know the data the component needs? Is that really necessary? And not only that, what happens when the data needed by the clients differ? Imagine we are Facebook or any other big application who have clients not only in desktop, but also in mobile and other screens, I guess. What happens when we want to render almost the same view, but the same view have more or less data depending on the screen we want to show? For example, we are in desktop, we want to show a lot of different data, but in mobile, probably we want to show a little bit less, right? So with this approach, at the end, you will have a lot of logic in your view, in your Django view, and it was not very easy to maintain. So we decided that the best idea is just let the client, let the component decide the data it wants. So we will expose some models from our backend in this through some HTTP endpoints, and the React components will consume this data. So as you may guess, I'm talking about REST APIs. But REST APIs, as probably all of you know, have some limitations. We have different endpoints per type, so different URLs per type. Imagine we have a lot of types, so we need to do a lot of requests for have this data. Also, if we use Hypermedia, for all the ones that you don't know what this is just pointing a URL when we have nested resources. That will mean that we have more HTTP latency. And on top of that, the pagination will only work for the global object. So what were the real consequences of using REST? When we render a page, we are not rendering just one type. A page involves a lot of different types. Imagine we are Facebook. We want to render a profile, which is a type. We want to render photos, news. And if we take the REST approach, we will end having a lot of HTTP requests. So after that, also, we need to integrate the data that we take from server. We need to integrate into our client code. So that means we will have to create Flask stores if we use the Flask architecture. And sometimes, you know, like the data we have in server, like the client could know in some way that. So we guess what was the solution, the obvious solution for the first two bullet points is just like solve the network problem, the HTTP latency problem. So just let's glue everything together in just one API endpoint. So if we are requesting, for example, just the data for a user, friends for this user and the company, we will glue everything together in just one API endpoint. So again, this is how our development process looks like if we want to add one field or one data into the component. We have to go to a component, change the layout to use this new data, and then we have to go back to the server API to change the API again. So again, the same question, why does the server have to know the data the client needs? So in conclusion, we want to let the component decide the data it wants and resolve it in just one HTTP request. Hopefully for us, two very different companies try to solve this issue at the same time. We got on one side Netflix, who released Falcor, and almost at the same time, Facebook released GraphQL. So let's gonna research a little bit how each one is resolving the content and how we can work with each one. So for example, if we want to have the data, the following data, we want to have the username, user company, and the name of the user friends. This is how we have to request through Falcor. So we specify the data we want through some paths, and the result data that we will have looks like a JSON graph. So we just have the fields with the data we want, and then, for example, for friends, we'll have an array of references inside the same JSON. And this is how the same request or the same query would look like using GraphQL. So we are requesting a user, the name of the user, the company of the user, and the friends of the user. And for each of these friends, we are requesting the name. And if you look closely at the response, it's like the same query that we are doing, but filled with data. So a GraphQL query is just a JSON without any data. That's the keys that we want. So what are the main differences between GraphQL and Falcor? GraphQL is a query language, as you can guess. Falcor is a library. I guess Netflix took this approach because they thought it could be easier for the developers to adopt the library, because sometimes developers, we are scared of like new things, new languages, and that could be like an easier way. But sometimes developers, we have no idea what we want. Also, Falcor response, as I said, is modeled as a graph. And GraphQL response is just like a tree. What that means, actually, if I have one friend and I'm retrieving data for me and my friend, and we share one friend in common, this friend in common will be, the response will have twice in the GraphQL response, and in the Falcor response, we only have this data once. So it's more reasonable, I will guess. One very powerful thing about GraphQL is it allows introspection. And with introspection, we can have a lot of different things. We can have validation for free. And we can have a lot of different things that I will research later. Also, GraphQL fields accept arguments. Falcor paths do not. What that means? Actually, we can see as a GraphQL field is like a normal function. So we pass arguments to this function, and we can play with the content, with the function inside. So at the end, we chose that GraphQL were probably the best path to take for us. But we have one problem. There was only one JavaScript implementation, and our backend, as I told you before, was in Python. So what we can do here? Option one, we can use the JavaScript implementation to wrap our REST API. This is a good approach, but doing this, we can lose some context. So the next option was just port the JavaScript implementation into Python so we can use natively in our backend. And that's great. Hopefully for us, some people start porting the JavaScript implementation into Python, so it was not very difficult to start with. So let's start with one example. If we are querying the user with the ID 1, and we want to get the name, company, and friends, and of these friends, we want to get the name, and we want to get the following response, this is how we have to create the schema in GraphQL. So we have the query type, which is the root object that we are querying, and this query type have a user field on it. The user field accepts an ID as an argument, which is a string, and returns a user type. User type have, again, name, company, and friends on it. And friends is just returning an array, a list of users. So this is how the implementation looks like in Python when we have to do it. So we have the user type, the query type, and we define some fields on top of that. However, if you are Python guys, you will see that that code is not very Pythonic. In fact, it's not very easy to work with. So shouldn't create a schema really be more simple? I want to be happy to work with GraphQL. I don't want to see this like there is some kind of overhead and I don't work like happy with GraphQL. So because of that, I create the Graphene Python framework. Graphene is a framework for Python that lets you use GraphQL very easily. That's the reason Brent do the Graphene joke. So what were the main goals of Graphene? We want to achieve simplicity. Also, we want to be fully compatible with the spec. So the same things that you could do in the JavaScript implementation, you could do it in Python too, with Graphene. Also, we focus on the syntax. We focus on the way we want to use Graphene. And only when we know how we want to use Graphene, only then we implement it, and not the other way. And also, we use it and we make it better with the help of the community. So this is how the first prototype looked like. We have a user type and a query type, and we define some fields in it. We have name, company, and friends, a user in the query. Also, we define how we want to resolve the user if we don't want to use the default one. And we have ID, which is an argument. If you look closer to this, we can see that ID is an argument who have a string field on it. So it's an argument with a field with a string. This really doesn't have any sense. So we went into our second prototype. We have a user type, a query type, and this type, we remove the fields from the type definitions. So actually, a string is a string, it's not a string field, and a list is a list, not a list field. And we can reference to the own object that we are using. Also, we move the resolver into the class, so you don't need to specify all times what is the resolver, kind of like pointing that, and it's much easier and pleasant to write. And again, if you look closer, we are defining a lot of times when something is a field or when something is an argument, but in fact, should be very obvious. So one type is a field when it's inside an attribute of a class, and one thing is an argument when it's inside a field. So we went into our final prototype. If you read closer this, you can see that it's very easy to know what's happening. And the types, we have a user type, a query type, user with name, company, and friends, and the user field in the query. So that's very easy and pleasant to work with. So what are the features of Graphene? It's very simple, concise, and powerful. Also, we have built-in relay support. So you can start playing with your frontend quite easily. Also, it's very well tested. Thanks for that, we were able to pass through the first prototype to the second one to the final version without doing any breaking changes. And the community really loves that. Like, we support our community. Also, one thing our community loves is we have automatic mapping from Django models. So actually, you don't need to redefine all your data and all your types again. You can actually just plug in there, and it will work with no effort, and also for SQL Alchemy. One thing I'm more proud of is the playground. I was wondering if I can make Graphene work in the browser. However, I have one problem. Python doesn't run on browser. What I can do here? So hopefully for me, there is one Python interpreter in JavaScript, and I just plug in Graphene into that. So you can just start playing in your browser with Graphene in the following URL. I will put an example so you can see how it works. So we create a user, which inherits from object type. We create a name on it, which is a string. Then a company, which is, again, a string. And then we create a list of friends, which is a list of self. In this case, self is just referencing the own type, the user type. And then we create the query type, which is, again, an object type. In this query type, we have a user field, which is just referencing the user type. And we specify that we have ID, which is just a string. And then we define how we want to resolve the user. In this case, just for the demo, I will return a random user, which is probably, you know, Peter Griffin. I think just put Peter, but it's the same. So friend, Peter have no friends. And then we define the schema that is englobing this query. The schema usually also have mutation and subscriptions, but I want to keep this easy. So then, once we define the schema, we can start querying it in the browser. You can do it in your own backend, but that's much easier. So if we query it, it will actually not work because we are requesting friends, and friends is returning a user type. So we have to specify which fields we want. In this case, the name. So we got this working. Isn't that great? Woo, perfect. So again, we are going to refactor a little bit. For example, we are going to create a map of users, defining which user, which ID have certain user. And we are just going to play with it a little bit. So we change from string to integer, and we get the ID from the arguments, and then we get the user who have this ID in the table. So if we play it right now, it will return null. That's because we are not putting any ID on it. So there is no user with ID null. And in this case, with the ID one, it's working perfectly. So this is how the demo works, but you can write any Python syntax on that. So that's great. So if we go to a real-world example, you can, how many of you have seen the GraphQL JavaScript Star Wars API implementation? Some people? OK. So if you go through the schema, you can see how just the schema has 2,000 lines of code. And that's not very easy to maintain, is it? Just the same schema made in Graphene, it only has 150 lines of code. And you can check it. It's online, it's open source, it's perfect. Yeah, I love my framework. So what are the upcoming features that I'm working in Graphene? We'll have live queries. What that means? That means that you will only query once the data you want, and your interface in any of your clients will change automatically once the data changes in the backend. So you don't need to worry about how to integrate the data from the backend to the client side once the data is changed somewhere. Like Meteor, but better, I will guess. Then we plan to add query complexity limit. So for example, you cannot make very harmful queries into the system. And we want to add Mongo Engine support for these people that use MongoDB. But what happens if your backend is not actually in Python or JavaScript? I have good news. GraphQL is almost implemented in any language. If your backend is in Scala, you can use Sangria. If your backend is in Ruby, you have GraphQL Ruby, and also for Go, Elixir, and almost any language. I believe Facebook will open source at some point the Hack implementation. I guess will be not very short time, maybe in a year or so. You will have to ask them. But why you should use GraphQL in your backend? Based on my own experience, GraphQL is much easier to maintain than REST APIs. Because of the introspection system, you can have one-click documentation and UI for free with no extra effort. It's not that great, like how many time we spend just like creating documentation for our own API, and how many time we have to say to the developers how they have to use or query our data. With GraphQL, we don't have to do that longer. It's very easy to query. Also, because of Relay, you can do a very quick integration with your front end. And at the end, as you don't need to change, as you, front-end developer, you don't need to go and change the backend all times you change something in the front end. The development process is much faster. It's much leaner. You don't need to go to the backend guy and say, like, please, I need this data. You can actually query it. It's much simpler. So I want to ask you one question. How many of you were disappointed of parse closing? 3, 4 people only? I were really disappointed. But when something closes, a new opportunity arrives. So today, I'm announcing Resolver. Resolver is a backend as a service system, much like Parse, but with one difference. We'll have live queries like Firebase, and will be built on top of GraphQL. Also, you will be wondering why is .cloud. And the main reason is because .com, .net, .io, and even .co were taken. Yeah, that sucks. So this framework is, thank you. So this framework is based on Graphene and will be completely open source. So you can either use the backend as a service that we will provide, or you can plug it in your own backend. So it's not that great. Thank you. Hope you enjoy it.
OK, let's take another break. And we have a pretty packed afternoon with 3 consecutive talks at the end of the day. So get your breaking in now while you can. All right, welcome back, everybody. So I just want to clarify a couple of things first. I think I maybe confused people a little bit when I talked about the reception earlier. So if you have your conference badge around your neck right now, just keep that. That's all you need. So that's it. So from 6:30 to 7, we're going to have 3 express elevators that are going to take you from the lobby level up to the 36th floor, which is where the reception will be tonight. We're going to have Tom Okino, aka DJ Tomo, spinning some tracks for us tonight. I don't know if that's the terminology. Yeah. We also have some leftover t-shirts and lanyards, so at the end of the day, you can go and ask at the desk out there and someone will give you that if you want it. Okay, our next speaker is Bhuvan Khattar. He used to work at Facebook, and he still works at Facebook, but everyone knows that too. But he actually, he actually did used to work on the Relay team and does not now, where he started focusing more on performance. And that led him to the JS infrastructure, or rather performance infrastructure team. And ultimately that led him to this stage right now. So let's give him a big round of applause. Bigger. Bigger.
Hey, I'm Bhuvan, and as Brent just said, I work at Facebook on our JavaScript performance infrastructure team. And today I'm here to talk about some of our efforts to make initialization faster for large and growing JavaScript applications. But before I sort of get into the more interesting parts of this talk, the aforementioned efforts to speed up application startup, let me actually sketch a scene that sort of highlights the performance problems that actually led to these efforts. This will have to be a verbal sketch, though, for I am nowhere near as skilled at drawing as Lynn Clark was yesterday. so bear with me. Okay, so the scene sort of begins with us building a web application. For a client-side functionality, we start off with our favorite JavaScript frameworks and some basic application-specific JavaScript modules, our React components, and some other business logic. Now, we need to somehow deliver all of these modules to the client. If we delivered each module in a separate file, downloading them would probably translate to a lot of HTTP requests, and the overhead of all the round trips to the server would slow down our application's initialization. So in order to sort of reduce that overhead, we could put all of our modules into a single file. And we could even automate the process of doing that by introducing a build step that determines all the modules that are actually required on the client side. We simply specify an entry file, which we then statically analyze to extract all of its dependencies, and then we repeat that process recursively to obtain all the modules that are required for a client-side functionality. So at this point, the byte size of this one file with all our JavaScript modules is pretty low. And our application's initialization performance is not really something to be worried about. Over time, though, we add more components and business logic to our application. And slowly but surely, the size of our custom code starts to overweigh the frameworks, and downloading that one single file with all of our JavaScript modules is now sort of a bottleneck to initializing our application. So with JavaScript on the web, we're really in kind of a unique position where we have to download, parse, and execute all of our code every single time a user reloads our application. Maybe browser caches help improve repeat visits, but only to an extent. Having to download, parse, and execute a large JavaScript file every single time a user tries to use our application is really not ideal. Imagine having to download an application from the App Store each time you wanted to check your email or the weather on your phone. That sounds ridiculous, right? But unfortunately, that is kind of how web applications work for the most part, for now at least. So we have to go to great lengths to ensure that our applications actually start up pretty quickly. And thinking about the problem from earlier a little bit more, we realized that not all of our JavaScript modules are actually used for the initial render. So it seems kind of wasteful that we're downloading all of them up front when only a small fraction of them are actually used. So perhaps we break down our single JavaScript file into a few smaller files. Say one file with all our core modules that are used across all the routes, and then some other files, each with modules specific to unique to a specific route. And then we even managed to largely automate this entire process to create these smaller files by specifying unique entry points for each route, and then just using static analysis to separate out the route-specific modules. And then once again, we sort of reach a stage where initialization performance for our application is not really a concern. But the story really doesn't end there. Our application does keep getting larger and more complex over time. The lines that once helped us divide our modules across different files have now really started to blur as more parts of our application reach into one another. We also have more routes than before, and our code has a lot more branching. Because of the complex features that we have and the increasing number of A/B tests, these branches keep getting heavier and heavier in terms of the dependencies that they pull in. And all of our users sort of end up downloading the dependencies for each one of these branches, even though they only use a small fraction of them. And what do we really do now? What are our options? Our dependency graphs are far too dense at this point. Any solutions that would relate to creating multiple alternate versions of these dependency graphs for different sets of users, perhaps each with some of the edges that are not taken based on the A/B tests the users are in pruned away, would probably not scale very well. Because even though the branching might grow linearly, the number of alternate dependency graphs we will need to generate will grow exponentially. And very soon, it would be next to impossible to generate all these alternatives. And that's sort of the end of the sketch. In the last frame, we sort of see ourselves staring down a crossroads, unsure of which way to go. We want our application to be richer and to have more features, but at the same time, our application startup performance is very important to us. And if you've ever worked with JavaScript applications of a non-trivial size, you probably related with some of the parts of the sketch. Now, let me get into the more interesting parts of this talk. By using the scene as a reference point, I'm going to walk you through some of the ways that we at Facebook have dealt with being at a similar crossroads. At Facebook, we did not want to compromise on either of the issues. So we've been building abstractions and infrastructure to get rid of the fork in the road altogether and improve our application's initialization performance, even in the face of increasing complexity. As we saw earlier, one of the first bottlenecks in web applications initialization was the downloading of JavaScript. So one of our first goals is to minimize the amount of time spent in doing so. Sadly, there really isn't a one-size-fits-all solution over here. There's a lot of factors that affect the amount of time that we spend downloading JavaScript. The overall byte size for JavaScript, the browser's caching static resources, the number of files that we need to download, the advantage that we can take from parallelizing HTTP requests, and the round-trip overhead of each one of them, just to name a few of the factors. I'm not going to get into the intricate details of the trade-offs involved here, but I'll quickly jump into some of the things that we do at Facebook to minimize the JavaScript download time. So first, let's take a look at how we combine and divide our JavaScript modules across multiple files to reduce the total byte size and take advantage of browsers' resource caching. On a high level, we break down our entire set of modules into subsets, which, for simplicity, let's assume are non-overlapping. Each of these subsets represents a JavaScript file with a bunch of modules, and let's call that a package. Each package contains modules that are likely to be used together, and then we automatically generate an optimal configuration of these packages. And in order to generate this optimal configuration, we actually use machine learning algorithms that work to maximize the resource download efficiency across all of Facebook.com. The algorithm that does this is the algorithm actually does this based on historical data of which modules are used together and a few other constraints. I'm going to call out two of the more important ones. The first one is minimizing the amount of extraneous bytes that are downloaded. We don't want to download JavaScript modules for a page load that we're not going to use. And the second is keeping the number of parallel HTTP requests reasonable. We want all the modules required on a page to be divided across more than one file, so we can take advantage of parallel HTTP downloads. But at the same time, we do realize there's an overhead that comes with each round trip, and we don't want that to slow down our application. So as I mentioned earlier, this isn't really a one-size-fits-all solution. The process of packaging that I just described is designed to maximize site-wide efficiency. So pages that get accessed more often, for example, the newsfeed in case of Facebook.com, will benefit more and probably have better startup times than others. Now, that sounds well and good, but I left something critical unexplained. I mentioned that we used historical data which modules are used together, but I never really explained how we figure out which modules are used together in the first place. In the scene that I had sketched earlier, it was pretty clear that simply using the dependency graph obtained through static analysis was not very helpful at determining which modules are used together, especially once the graph grew dense and we had far too many branches. For instance, let me bring back this example of an A/B test. It's really not obvious from static analysis that there is an exclusive OR relationship between feature new and feature old for any single user, because which one of the branches gets taken really depends on runtime data. But servers actually do have this runtime data when processing a request, which puts them in a great position to help decide which branch gets taken. So we take advantage of this fact by employing a famous trick. We add a level of interaction. Let's see how we do this. We move the branching code from our client-side code to the server side, and then we introduce an alias. Now, static analysis picks up the alias feature as a dependency of the module in our client-side code, but neither feature new nor feature old make the dependency list. And then on the server, whenever we're processing a request whose response would include feature as a dependency, we execute this branching code to resolve the alias to either feature new or feature old. This leads to only one of feature new or feature old being downloaded by the client, and it also correctly informs our packaging system that feature new and feature old are never used together, which leads to more efficient packaging for future requests. So it seems like by using our servers as more than just a collection of API endpoints for reading and writing data, we're able to solve a performance problem. And we don't just limit expanding the server's role to just support module aliases. We actually do a whole lot more. Let me introduce another way in which we use our servers to improve our client-side performance. Instead of using JavaScript modules to determine the entry point and dependencies required for each route, we actually generate these entry points dynamically on the server. So in our server-side controllers, we indicate the entry point into execution on the client side using what we call JS calls. If this code sort of looks alien to you, it's because this is PHP code. So for example, this JS call over here, when executed on the server, results in the following being included in the response. So not only does this help us co-locate the logic for handling a request and determining the exact set of JavaScript dependencies that need to be downloaded by a client, for example, in this case, foo and all of its dependencies, it actually also lets us stream the initial data that is needed to bootstrap our application. Typically, client-rendered applications end up working something like this. The browser makes a request to the server, which sends a response that leads to JavaScript being downloaded and executed. And then when this JavaScript is executed for the first time, the browser sends a request to the server asking for initial data for the application, which the server then generates and responds back with. It is only at this point that we can finally render and initialize our application. But with JS call, we can actually eliminate the second round trip and speed up our application's initialization. It also helps us reuse the context for a user on the server and reduce the total amount of processing, since HTTP's stateless nature would have required repeating a lot of work on the server for the second round trip. And this streaming of initial data can be made even more seamless with Relay, where the set of initial data required can be determined easily by extracting the GraphQL queries for that route, eliminating the need to create any route-specific controllers on the server altogether. So I'm sure by this point, there's someone, at least some of you in the audience, have come up with the idea of isomorphic JavaScript and using server rendering as a solution. I think isomorphic JavaScript is great, but it's definitely not a catch-all solution to client-side performance problems. I can see why it might be tempting to think that it is, because until a few years ago, everything on the web was actually server rendered, and things were pretty fast back then. But let's not actually fall victims to any logical fallacies here, because web applications were also much simpler back then. They barely had any of the client-side interactivity that we do these days. So we found that server rendering does not actually solve the problem of slow application initialization, and here's actually why. For any typical server-rendered application, a request gets handled something like this. Upon receiving the request, the server generates the data required for the application, and then executes all the JavaScript that would have been executed on the client on the server. And once that execution is completed, the server sends down the markup that resulted from the execution. But that alone isn't enough. The client also needs all the JavaScript and the data to reconcile its state with the server for it to actually be interactive. And there we go. So yeah. And we could potentially improve things a little bit by slightly parallelizing the downloading of JavaScript as we were generating the markup. But at the end of the day, server rendering is still less efficient for most scenarios. The server rendering alternative leads to redundant work where the JavaScript executed is both on the client and on the server. And we're downloading more bytes because now not only do we have to download the JavaScript and the data, but also the markup. And we have an overall worse time to reach interactivity on the client side. Anyway, so let's revisit the goal of minimizing the number of JavaScript bytes that are required to initialize our application. With JavaScript module aliases resolved on the server side, we were able to avoid downloading extraneous code that we knew would never have been executed on the client. So the amount of JavaScript that needs to be downloaded is now lower, but we still find that it is high enough, and it is a significant bottleneck to our application's initialization. Let's see how we can reduce this even further, reduce the amount of JavaScript needed to be downloaded before initialization even further through this example. Let's consider the share dialog for Facebook stories that pops up when a user clicks on a share button. We can improve the startup time of applications in this case by taking advantage of two things. Number one, the share dialog and its dependencies are actually not required for initialization. So we only need to download them when the user actually shows any intent to use the share feature, perhaps by clicking the share link over here. And we also do not need to synchronously respond to the click by displaying the share dialog right away. We could show a loading indicator while we asynchronously downloaded the missing dependencies in the background. And once we had all the dependencies, we could display the share dialog. To make this sort of asynchronous handling easier, we have an API that we call Bootloader. Bootloader allows us to differentiate between asynchronous dependencies from synchronous ones. So in this case, by changing the require to bootloader.loadModules, we no longer need to download the share dialog initially as a dependency that would block initial JavaScript execution. Instead, we just inform the client where to actually find share dialog in its dependencies in the initial response. And then whenever the bootloader.loadModules call is actually executed on the client then downloads the share dialog and its dependencies if they're not already available, and then executes the corresponding callback once they are. So we now have this API that sort of abstracts away the implementation of figuring out which dependencies are required and not available, and then downloading them. But there's still sort of some boilerplate the developers need to write to display a loading indicator initially, and then swapping it out with the real component later. We reduced this boilerplate to make the use of bootloading even more seamless for React applications by introducing a higher order component that looks something like this. I know that's a lot of code to put up on a slide, so in case you don't feel like reading it, it simply manages displaying a loading indicator initially on mount when the component is mounted, and then replaces it with the actual implementation once the component has been downloaded. So with this, in order to make any part of a React tree to be loaded asynchronously, as a developer, I really need to change two lines of code. I can change the require over here to a wrapper that uses the bootloaded component, and then replace the component in my React tree, and I'm done. So let's actually look at another example that we commonly see in our React applications. Components usually conditionally compose a different subcomponent based on the current route. Somewhat similar to the case with the A/B test example that we saw earlier, only one of these components will actually be used on a route, but static analysis would include each one of them as a dependency, leading to extraneous bytes being downloaded for the initial page load. Yes, we could use the bootloader API to download these, but that would require an additional round trip to render it initially, and then one more at each level of nested route, any nested route-based conditionals from any subcomponents. To get around that, we actually built an abstraction that we call match route. We can replace the branching in our code in this example with this match route syntax over here. It's a lot more declarative than the alternative, and then also allows us to gather more information during static analysis. Now, when we're statically analyzing and collecting the dependencies for the current module, we skip the dependencies inside of the match route call. Instead of collecting these as a dependency for the current module, we mark them as a dependency of the corresponding route. So whenever a request comes in for a route, we include the response and the dependencies of the point of entry and of the current route. This ensures that the dependencies for the branch that will be taken by any match route call executed on the client side are always available, even though the dependencies for other branches might not be. And then whenever we're making an asynchronous transition from one route to the other, we bootload the dependencies for the new route before re-rendering, ensuring that dependencies required for the alternate match route branch taken this time will also be available. And with relay applications, we can take this a step further. We can download both the JavaScript module dependencies and the data dependencies for rendering a new route before executing the code to render it. We really love abstractions like these because they allow us to fall into what we call operative success. Not only do they provide a great developer experience, but they also lead to creating more performant applications by default. So far, I've talked about a bunch of ways that we speed up our application startup by reducing the byte size and the number of round trips that we need to make, and also incrementally loading parts of our application. But downloading JavaScript is really not the only bottleneck to application startup. There are other sources of wasted time that we could potentially recoup performance from. Once the JavaScript has been downloaded, it needs to be executed. Let's actually take a quick look at how the execution works by diving into how module systems like CommonJS work. When we write a module, our module system actually puts a wrapper around it before sending it to the client so that the code is not executed immediately, and we can reference the modules later using a function like require. So when a large module gets required for the first time, when a module gets required for the first time, the corresponding module factory is actually executed, and whatever is the result of module.exports at the end of this execution is the value that gets returned to the require call and also gets memoized for future requires of the same module. Since we usually list our dependencies at the top of a file, this means that before we can execute anything that we intended to do with the module for the first time when we're using it, we end up doing a depth-first initialization of the entire dependency graph underneath it. You can sort of imagine how this might be wasteful for large dependency graphs where only a small part of them is actually needed to be used. And I should have made this actually go by itself. OK. So we make this much better by automatically transforming our modules to inline the requires call wherever the modules are actually referenced. So when we do something like require of a.b, for example, we will now only initialize modules A and B, assuming that b.foo does not actually require any other dependencies. We call this transformation inline requires. And yes, developers could actually do this manually when writing their code, but that makes it really hard to quickly look at a module and determine all of its dependencies. And it also adds to the cognitive overhead that's actually required on a developer's part when writing this code. The automated transform really makes this seamless. Once again, there we go. So with inline requires and lazy execution of module factories, we've seen the amount of time spent executing JavaScript before our initial render drop by around 10% in both our web and React Native applications. And we've also been able to use this to make our JavaScript unit tests run almost twice as fast by making module initialization and mocking lazy via the inline requires transform. But this does sort of come with trade-offs. The lazy execution of module factories means that we cannot rely on any side effects to run eagerly. And having cleaned up a lot of these side effects from our code base just last year, let me tell you, it's kind of hard not to. Even something as simple as a top-level statement in a module that subscribes to some sort of an event system for updates, if not executed eagerly, could end up breaking our entire application. So if you're going to use lazy initialization of modules, you need to ensure that your application explicitly executes any side effects that need to be executed eagerly. There's also another problem that comes with lazy execution, and it is that lazy execution could lead to deferring some execution until later. So, for example, the initialization for a bunch of modules could end up being deferred until just after a user interaction, which would end up being a bottleneck to us responding to that user's interaction. But we do have a solution for that too. In profiling our JavaScript applications, we see a lot of idle time chunks between execution. And lazy initialization via inline requires often further increases these gaps. We take advantage of these gaps using something like request idle callback to schedule work during idle time left at the end of an animation frame. We queue up modules whose initialization had been deferred earlier via inline requires to be initialized during these idle gaps. And we call the strategy eager requires. A combination of inline and eager requires have really allowed us to be smart about managing our JavaScript execution. We can do the least amount of work necessary when time is of the essence, and then during any free time, proactively catch up to the work that we had deferred earlier. So these were a few of the ways that we improve application performance at Facebook. I know I condensed a lot of information within this talk, so I'll quickly recap. I began by describing how we automatically segregate our JavaScript modules across multiple files to improve site-wide download efficiency. And then, by using this server as more than just a collection of API endpoints, we're able to minimize downloading extraneous code and dynamically generate entry points into our client-side JavaScript execution, and also generate and stream any initial data required by our applications for the initial response, with the initial response to reduce further round trips to the server. We also minimize the amount of JavaScript that needs to be downloaded by incrementally loading our applications, by adding support for asynchronously downloading dependencies for handling interactions, and by classifying modules as dependencies of routes instead of just other modules. We make this incremental loading even more seamless for route transitions. Another way that we improve performance is by managing JavaScript execution better. We lazily initialize our modules by default and then eagerly recoup any losses that occurred from the laziness in a non-blocking way by using request idle callback. And of course, these efforts don't mean that we're done and have completely solved the problem of slow application startup. At Facebook, we believe that there's always more to be done, and there are always boundaries that need to be pushed further. We're actively investing other ways to further improve performance, and in one of the talks from yesterday, Aditya showed us how service workers have been instrumental in Flipkart Lite's success. And using service workers is something that we have started looking into as well. And to address a likely follow-up from this talk, how can I take advantage of all the things that you talked about in my application? I'm afraid the answer might not be the one that you were looking for. The implementation details for most of these ideas are bound to be infrastructure specific, and our current implementations, for the most part, actually are tied too intricately with our infrastructure for us to separate out. Nevertheless, I did try my best to provide all the necessary information that you might need to implement these into your application's infrastructure. And I would be more than happy to answer any questions that you might have. And I'm really excited to see all the cool things that you might create with the information from this talk. My Twitter handle is VoidianValue. I look forward to hearing from you. Thank you.
Great. All right, let's move along. Our next speaker is Jamison Dance. So Jamison Dance is the co-organizer of React Rally. It's a conference in Utah, happens in August. And he's actually one of the few people whose last name is also a top-level domain. And he actually owns jamison.dance. That's pretty lucky of him. Yeah, so today he's going to talk to us about the Elm programming language. And yeah, so here's Jamison.
I'm good, Ryan, thanks. So, hi. Brent already talked about this, so I'll skip over most of it. Jamison.dance, thank you. I do a podcast called JavaScript Jabber where we talk to smart people about cool things they build in JavaScript. I'm Jurgensen on Twitter, React Rally, and because there are a few things that make dads happier than forcing groups of strangers to look at pictures of their babies, here's my baby. Thank you, thank you. That's the correct response. I appreciate that. I want to step up on a soapbox very briefly and talk about the word isomorphic. This is the Wikipedia page for isomorphic. It's got a lot of words, so we'll zoom in on some essential parts. For most algebraic structures, including groups and rings, a homomorphism is an isomorphism if and only if it is bijective. Now, I don't know what any of those words mean. I just highlighted stuff at random. But I know what they don't mean, which is server-rendered JavaScript. So I just want to, in a spirit of love, suggest that we not use the word isomorphic to describe server-rendered JavaScript. That'd kind of be like me making a library that replaces all the images on a website with pictures of my face and calling that React.js. Like, that name is taken already by a different thing. So let's, I don't know, server-rendered, universal, let's use one of those. OK, off the soapbox. I want to talk a little bit about the rise in the size of JavaScript applications. This is a graph showing the average JavaScript payload from 2010 to 2015. It's a little hard to read, but it says that the average size has gone from 100 kilobytes to about 360 kilobytes. So it's more than tripled. And I think this reflects the growing richness of experiences that people are building in JavaScript. They're sending more JavaScript down to the client to do more things. Interestingly, if you extrapolate from this, in 2047, we'll download a petabyte of JavaScript. So prepare your Webpack loaders for this reality. I think that last talk will actually help a lot with this. So in response to this, larger applications being built in JavaScript. The JavaScript community is amazing. They build all these cool tools. GWT came out in 2006, I think. It was a Google effort to write in Java and transpile to JavaScript. It's an attempt to answer the question of how do we build these large, complex applications. Don't use it anymore, though. Require.js was an early kind of module loader. I think it was 2009. Backbone, sorry, this is the Google Closure compiler. It was 2009 as well. And it also did some module bundling and minification and concatenation and some type checking as well. Angular, I think the first commit was either December 31st, 1969, or sometime in 2010. They might have some date bug going on in their Git history. Backbone was actually after Angular. it was also 2010. And then Ember was, I think, 2011, React 2013. And then all these other tools to help. There's Webpack and NPM and Grunt and Gulp and Browserify and Babel and ES6. But the underlying substrate of all of these tools, the underlying assumption is JavaScript, right? The assumption is you are building web applications in JavaScript. How many of you have heard of this phrase, rethinking best practices? Okay, lots of you. Shout out to Pete. He's somewhere around here. This is from a talk he gave introducing React in 2013. And I love this phrase because the first time you hear it, it kind of sounds like the ramblings of like a stoned out teenager in his bedroom. Like, what if we replaced all the semicolons with monkeys? But that's not the idea. The idea is actually, because you do something, that doesn't mean that's the best way to do it. That's just the way you do it. If you examine some underlying assumptions, you might come up with a better approach. And that's what React did. And people thought it was not good. And they were wrong. It is good. And in that spirit of rethinking best practices, I want to talk about the Elm programming language. How many of you have heard of Elm? A lot of people. Cool. How many of you have used Elm at all, like written any lines of Elm code? OK, fewer people, but still some. Awesome. So Elm is a functional programming language that runs in the browser. It's not JavaScript. It transpiles to JavaScript. This isn't a talk about how to write Elm applications. I don't think I can teach you in half an hour how to actually go out and build an Elm app. This is why you should look at Elm for writing applications, why you should teach yourself. So to do that, we're going to look at some problems that we encounter in JavaScript. This was from Texas JavaScript in 2013. They actually put up on the marquee of the theater, undefined is not a function, because that's like the most JavaScript phrase you can think of. How many of you have had runtime errors in your JavaScript? I see some hands not going up, and I want to talk to you. Yeah, or someone shout out liars, but I didn't say that. Yeah, this is a problem. This happens all the time in JavaScript. This is a dumb function. Like, you can clearly tell this is going to throw an exception. This is a stand-in for more complex code where the error is hidden deeper, but that won't fit on a slide. So here's our example. You call this function foo, you pass in a number. If the number is greater than 10, it returns a string. Otherwise, it implicitly evaluates to undefined, and then you call to uppercase on the result. And if you pass in a number less than 10, it'll explode because you can't call to uppercase on a string. Or on undefined, I'm sorry. And there are a couple different solutions to this problem that the JavaScript community has come up with. There's one class of solutions that's kind of the know when these errors happen. And there are services like Track.js and Sentry and Raygun and a bunch of other ones. None of these people gave me money, by the way. They were just the easiest logos to find. They'll aggregate your client-side errors in some service that you can then look through and figure out where they came from. There's also the awesome Chrome developer tools. These are really great tools that will help you write better code, and I recommend them. But I'm a little sad that I live in a world where someone can make a career out of tracking errors that happen in your code, because it means they happen so much. It's a little bit like you have a house, and it's a really ugly-looking house, actually, when it's blown up on the big screen. But it's a nice house. It's our house. We like it. And then it lights on fire. And someone comes and tells you, hey, Bob lit this house on fire. And you're of two minds at this point. One part of you is like, thank you, now I can go have a conversation with Bob and figure out what's going on here. But the other part is like, ideally my house would not be on fire right now, and you wouldn't have to tell me anything. And that's kind of the other class of JavaScript tools that I want to talk about, which prevent errors. This is stuff like ESLint, which does some style checking. It can also catch some like misspellings of variables or things like that. And there's also tools like Flow. It's been brought up a lot, and we'll talk about it more. Flow is awesome. Flow adds a gradual type system to JavaScript, and it can do sophisticated analysis of how values flow through your program to detect errors. Here's that same function we showed earlier as a reminder, and let's see what happens when we run Flow on it. So Flow tells us, call of method to uppercase cannot be called on possibly undefined value. That's awesome. Flow detected that sometimes this function will return undefined, and if you call to uppercase on undefined, it breaks. So Flow yells at us, job done. We can fix this bug, and our lives are better. Except there's one thing that gradual type systems do. It's a design decision. You can turn them off on individual lines or functions or files. That's because they were designed to run on existing JavaScript code bases. And there's some ways that people write JavaScript that are just hard to run through a type checker. So it allows you to gradually add flow over time to your project. And it's a good feature. So this is flow syntax added to this function. That :any after the closing paren tells flow this function can return anything. You can make no assumptions about it. It's basically like, go away, flow, I know what I'm doing. And here's what happens when you run flow on this code now. No errors. Well, there are still errors in this function. And this gets to, I think, an essential weakness in gradual type systems. They're awesome tools, but the fact that you can turn them off when you get frustrated, or when you get stuck, or when there's a deadline, or if you're new on the project and you don't quite understand how the tool works, or you're just having a bad day, that means that you will turn them off sometime. And then you'll lose that safety that these tools give you. There's another issue with them, which is related to this, which is code that's hard to type check is code that you're not going to type check. And that code is often the tricky, important parts of your application that you most need to type check. Because there's an out clause, you'll use it because you're a human and you're subject to human failings. So let's talk a little bit about Elm now. It's been 10 minutes and now it's time to talk about Elm. Elm has a static type system. And one consequence of that is you get no runtime errors in Elm. This is hard to explain in words how awesome it is, so I'm just going to make this text bigger. No runtime errors. And you can't opt out of the type system, which means that Elm can make very strong guarantees about how your code works. Let's look at some examples of how this looks. So this is Elm code. This is a function, foo. It takes in an argument num. So everything after the equal sign is the function body. And we're trying to rewrite the same function we wrote in JavaScript, but in Elm. So if num is greater than 10, then we return some string. In Elm, the returns are kind of implicit, so you don't have to type return. Let's see what happens when we run Elm on this code. Oh, it's a compiler error. I ran into something unexpected. I was looking for one of the following things in else branch. OK, so we forgot an else. You need to have an else. You can't have an if without it. Put that in. If num is greater than 10, return a string, otherwise null. Oh, there's no such thing as null in Elm. Sorry. Wow. I didn't expect applause there. Great. I agree. Here's the error that it gives you when you do this. Can't find variable null. And then I love how helpful it's trying to be. Like, did you mean num or list.all? Like, oh, Elm, you're trying so hard, but I did not mean either of those things. Thank you for trying, though. So let's write this in a way that works. So we have to return something. We can just return a string in the else block. And now this function will compile. Our program will not break. That's probably more important than this compiling. We won't have a runtime error. But this isn't the same behavior as what we had in JavaScript. In JavaScript, we either returned a string or we returned nothing. And I want to talk a little bit about how Elm's type system can help enforce this behavior. But to do that, we have to talk a little bit about the type system itself. So here's how you define a type in Elm. This is saying create a type named bool, and the possible values this type can take are either true or false. There's nothing special about the word bool or true or false here. These are just names you give to either the type itself or the values the type can take. This is actually how a Boolean is defined in Elm. It's just a type in the Elm language. It's not built into the compiler or anything. Here's another type that's a little more complex called maybe. And a maybe type kind of represents something that can either be empty or have a value of a certain type. So maybe a, that lowercase a, is a stand-in for another type. So a maybe of some type can either be just a value of that type or it can be nothing. And we'll show how it's used. This is how you do it. If number is greater than 10, then just the string, otherwise nothing. And now the compiler can run on this code, and it can help us make sure that we check all the cases, and we're not going to get nothing when we expect just and stuff like that. So as an aside, Elm has types, but you don't have to write the types out on your functions. It can figure them all out. If you want to, this is how you do it. the function name, and then the colon, and then the argument, and then that's the result. So this function takes an int, it returns a maybe string. Here's how you would use it. This is another function, bar. It calls foo and then runs a case statement on the result. So it checks if we get a just string back from foo, then call to uppercase on it, otherwise return the string whelp. And the cool thing to notice here is if we leave off that nothing check, then the compiler will yell at us. The case does not have branches for all possibilities. You need to account for the following values, maybe dot nothing. So the Elm knows all of the possible values that the type maybe can have, and it knows when you're checking some of those and not all of them. And this is awesome. Think of this in like a Redux app, right? You have all these types, these action types that you can have. What if you had a compiler that checked if you were misspelling one of these, or checked that you didn't handle a certain action type in your code? It's pretty great. So what would a React conference talk be without a Dijkstra quote? The competent programmer is fully aware of the strictly limited size of their own skull. I want my computer to do things that it can do well, so I can do things that I can do well. And the computer is much better at tracing the flow of values through a program than I am. I'm not going to think of all the edge cases. I'm just going to think of the happy path because that makes me feel better about my code. I don't want to break my code. I don't want to know if it's broken because that means I'm a bad programmer. But the computer has no mercy, right? The compiler will tell you, and then you'll fix it, and you won't have these errors. I need my brain space anyways to do something else, which is work on my startup, Uber for Cats for Dogs, which is serving the underserved dog man economy by delivering cats to them. We're looking for our first developer. If you're interested, we're actually not looking for a designer. As you can see, design is on lock. So, yeah. All right, I want to talk about another problem that happens sometimes in JavaScript, which is as applications grow, often they become harder to maintain. They get a little tangled. They're harder to add features to. They can get harder to debug, easier to break. I know that sometimes when I'm writing code, I just have this feeling that I don't know why, but I'm pretty sure in 6 months I'm going to hate the thing I'm doing right now. And the JavaScript community, because it's great, has lots of solutions to this. One solution is React. And React is awesome. I love React. I've been doing React for a few years, and I think it's a great tool. With React, you structure your app as a tree, components, right? You all know this. Pass data down, and then when things happen, you somehow pass stuff back up and then re-render the application. This is a great pattern. And you can build applications like this in JavaScript. But you don't have to. You can do whatever you want. You could build a library that searches Stack Overflow for keywords, so you type drop-down menu, and then it finds the JavaScript code in the post for drop-down menu, and then like evaluates that on the page, and build an application out of that. And nothing will stop you in JavaScript, except maybe your conscience. That'd be a cool library, by the way. If someone wants to write that, I would use it. In jest only. So the point is there are patterns in JavaScript, but nothing's forcing you to use them. So the React model is such a good idea that Elm actually looks very similar. The way you build applications in Elm is you have this tree of functions. You pass data down to child functions, and it renders out some UI. And then when some user interaction happens, you send data back up to the top. There's a top-level app state. You update the app state, and then you re-render the application. The difference is this is the way you build applications in Elm. This is the kind of accepted pattern. All of the community documentation, all of the core libraries is built around this pattern. So when you come into Elm, there's a lot of new stuff to learn, right? It's a new language. It's got new syntax. But you don't have to decide, how do I build stuff? Because that is already decided for you in a good way. And I think that's pretty powerful. Let's talk about another cool thing that's happening in JavaScript to help solve kind of issues with maintainability. How many of you have heard of stateless functions? A few hands. You might have heard of them called pure functions. Can anybody give me a definition of what a stateless or pure function is?
No side effects.
No side effects. OK, if you want to come up and give the rest of the presentation, because that was a really good answer. Yeah, no side effects. A stateless function just takes in input, and it returns output, and the output only depends on the input. This is a good way to build applications, because stateless functions are easier to test. You can just run them. You pass values in and assert on the results. They're easier to reuse in other places because they don't have dependencies. You don't have to mock anything out or set up complex layers of dependencies to reuse them. And it lets you build more composable and maintainable applications. So you can do this in JavaScript. This is a stateless function that adds two numbers, return a plus b. Great, it works. But you don't have to. You can do whatever you want in JavaScript. Nothing is stopping you from writing this, fire the missiles, and then add the two numbers. And let's look at what that looks like. I wrote this function, but I'm not quite sure what's happening. I mean, 1 plus 3 is 4. 5 plus 8 is 13. So things look OK so far, but there's something weird going on. So let's write this for loop and kind of check out the results. Oh, it turns out I don't know how to write for loops. Just call it a bunch and see if we can figure out what's going on that we don't understand. So we'll add the loop index together. And I have good news and bad news. The good news is that 99 plus 99 is 198. The bad news is the world has ended. All that remains of our shattered society are a few faded Uber for cats for dogs billboards to remind us of what we once had. So yeah, you won't do that. You won't fire the missiles in your add function, but you might do something that looks more like this. Say you want to track for analytics purposes, like marketing, big data, I don't know, buzzwords. Every time a user calls the add function, you could put in this function to record user addition. And it's going to send a request to some third-party service, and then you're going to big data your way to the cloud and all that stuff. And that's really convenient, right? Nothing in JavaScript is stopping you from doing this. But now you've destroyed the stateless nature of the function. Now you have to set up dependencies to reuse it in other places. Now you can't test it as easily because it's going to do this other thing when you call it. And yeah, so you can do this in JavaScript, but it might not be best for the long-term maintainability of your project. So Elm only has stateless functions. This is the way you write functions in Elm. There's really only a way to write the add function. You can add two numbers, add a and b. That's, I mean, yeah, you can see it. There you go. The Elm type system will actually enforce this. If you try and do a side effect inside of a function, it'll yell at you. Your program won't compile. So by making this decision for you, Elm is encouraging you to build applications in a way that's better in the long term. Let's talk about immutable data. How many of you know what immutable data is? It's come up a few times in the conference already. If any of you don't, the idea is that if you have some data structure, you don't modify it in place ever. You return a copy with those modifications applied. And there are libraries to do this in JavaScript. There's Immutable.js that Lee Byron, who's somewhere around here, wrote, and it's rad. There's Mori, there's a couple other ones. You can do it in pure JavaScript as well. Thank you, Sebastian, for letting us use the object spread operator, I think it's called. So update user score will take in a user and some points, and then this will return a new object with all of the properties of user plus this updated points property. So you can do this in JavaScript, but you don't have to. Look at how much shorter it is to not do that, right? Like, it's like the language is encouraging you to just mutate it in place. And maybe you don't know, too. Like, everyone is learning. Everyone's coming in at a different level. And there's a lot of stuff to learn. So the fact that you need to learn, hey, immutability makes my applications better, means that you might not know that at some point. Like, immutability is better for you. Vegetables are good for you. Sometimes you just don't want to eat your vegetables, too. Elm only has immutable data. Immutable data structures are built into Elm, and they're the only way you can interact with data. So here's how you would write that update user function in Elm. Update user takes in a user and some points, and then this syntax is just how you say modify this object. Take the user object, set its points field to this new value, and return that new object. So this is another case where Elm has these good ideas built in at the language level. Let's talk about one more issue that's come up in a couple talks already, which is, yeah, React tells you to structure your app as this tree of components. But this part right here, it doesn't really tell you that much. How do you actually get the modifications back into your app, right? How do you communicate state around your application? And again, the JavaScript community is smart, and they have lots of good ideas about this. There's callbacks, there's Flux, there's Redux, there's observables. We learned about some ClojureScript stuff that I forgot already. But there's lots of really cool ideas about how to do it. But they all have different trade-offs, and they also have the issue that you need to decide between each of these and learn it and figure out why it's better for your needs. So in Elm, the way you communicate state around your application is something called functional reactive programming. In JavaScript, it's like observables or RxJS or something like that. So here's kind of a model of an Elm program. You have some button that when you click the button, you want to toggle the color. So you have a function that takes in an observable, basically, and renders the UI. And then when the button gets clicked, you send an action on this observable. And then at the other end of the observable, there's this update function. There we go. This update function that receives the thing that came off the observable, and it receives the current state of the application. And then it applies that action to the state and returns a new state, kind of a new model. And then there's another observable hooked up to the output of this function that ends up calling your view function again. So you re-render your application with the new state of the model, and then our button turns red. And this is a thing you can do in JavaScript, and lots of people have done patterns like this in JavaScript. But the fact that it's built into Elm at both the language level and like the community level is pretty powerful, I think for two reasons. One, I think it's a good way to model applications. It's easy to build complex UI applications like this. But two, it eliminates this decision fatigue. There's no Elm fatigue because you just do the way the language has been designed to work. And that's a pretty awesome thing. And I think it gets at this idea that this trade-off between constraints and freedom. So I think the JavaScript community values freedom. There are a million different ways to do everything. NPM has 80 bajillion libraries on it or whatever, and that's awesome. There's a ton of different choice in JavaScript. But that choice comes with a cost, because some of those things are better for some purposes than others, and you have to evaluate all that and figure out what's best for you. If you have more guidelines, more constraints, you don't have to worry about making all those choices. And if you trust the designers to have made good choices, then you get to focus on things that are specific to your problems, to your application domain. I drew this helpful diagram. Why are you laughing? Are you suggesting I'm not an artist? This is like, what if someone tried to do code cartoons, but they couldn't draw? And this is the answer. They use Keynote to draw circles. So the green circle is the space of all possible programs, any sequence of characters that can be executed by any programmer, compiler, computer, whatever. There's some subset of that programs that are going to be good. And by good, I mean they'll be easier to modify. They'll be faster to update. They'll be less likely to have bugs. It'll be easier for new people to come in and learn them. And Elm has made design decisions that try and guide you towards some subset of good programs, where if you just do what's built into Elm, you'll be more likely to build good programs. And there's certainly a way to build bad programs in Elm. I have Elm code up on GitHub, and lots of it is bad. But Elm can guide you towards better programs. Constraints can guide you towards better design. This is like my thought leader slide, I guess. I don't know. So I want to come back to that Dijkstra quote. A competent programmer is fully aware of the strictly limited size of their own skull. Before we talked about this as not having to worry about how your values flow through your program, because the type system can help you with that. And I think this also applies at the higher level of language and framework constructs. If you don't have to worry about what's the framework du jour of like data modeling in React or something, you can focus on things that are specific to your problems, and you can solve those better than anyone else. And I think Elm frees you up to do that. Thanks, Dijkstra. That's him popping in to say hi. So there are some caveats. Everything has downsides. I don't want to give the impression that there's nothing, that Elm is perfect for everybody and there's nothing wrong with it. It has a smaller community. Server rendering's not quite there yet. If you don't use React Native, then maybe you'll be happy about this. There's no React Native in Elm. Elm does best when it can talk to JavaScript, and you can talk back to Elm from JavaScript, but it really does better the more of your application it controls. But I think most of these problems come down to the fact that it's still kind of early days for Elm. People are using it in production. Production ready is kind of a sliding scale depending on how bold you are and how much you're willing to commit to training and creating tools and stuff like that. So I would say For some people, it's definitely production ready, but it has some issues. Actually, this morning, somebody hooked up React Native to Elm, so I guess that one's crossed off. But I want to come back to my main thesis, which is that browser applications are growing. They're getting larger and more complex. The JavaScript community is smart and awesome, and they're coming up with great ideas and tooling to solve these problems. And I think Elm is what the JavaScript community is kind of evolving towards, but it's just built into the language. If you are interested in learning more about Elm, here's some resources. Elmling is the main website. There's a Slack channel. We did an episode talking to the creators. There are 2 really good talks. This is talking about how you do like side effects and talking to servers and stuff in Elm. And Let's Be Mainstream is a talk kind of about the philosophy behind Elm that I found pretty fascinating. Or you can just bug me on Twitter, and I will either answer your question or point you towards someone smarter who can answer your question instead. Thank you very much.
All right, well, this will be our last break of the conference. Make sure you do everything you need to do to be able to come back here and sit down for an hour and a half afterwards. Just wanted to mention, though, if you enjoyed that talk, remember Jameson is the organizer of React Rally. It's a really great conference, so you should definitely check that out. In addition to that, there's React Europe coming up on June 2nd and 3rd in Paris, so I'd highly recommend checking that out, too. All right, let's break. All right. Okay, here we are in the final stretch. Our next speaker is Tadeu Zagallo. He works at the Facebook London office on the React Native performance team. He's originally from Brazil, and he's one of the hardest working people that I know, actually, and he's also one of the most genuinely curious people that I know. He describes himself on his blog as a software engineer passionate about compilers. He's written about topics like building an x86 emulator in JavaScript and using assembly to profile React Native iOS. So, I guess what I'm trying to say here is you should probably start paying really close attention, right about now. And if you don't, you're probably going to get lost pretty quickly. So, all right, here's Tadeu.
Hello, everyone. It's been 1 year since React Native was announced as a way of unifying how we build web and native apps. You might have heard it before, learn once, write anywhere, or as Chirag put it yesterday, a horizontal platform. But the biggest motivation for creating React Native in the first place was that native apps feel better. They feel better because they are capable of using all the phone's resources. Things that are not available from the web browser environment, things that allow us to create more smooth and responsive apps. So React Native improved a great deal the native development experience. But we also want to make sure that users keep having a first-class experience. And for that, we are investing heavily in performance, because we believe that performance is key when it comes to a good user experience. So by the middle of the last year, we started a new team at Facebook, the React Native performance team. And our goal is to make React Native as fast as we can. And we believe that we can make React Native apps at least as fast as the native ones. And today I'm going to talk a little bit about what we've been working on. So to start off, I just want to take a couple minutes to go through a very quick overview of how React Native works. And as you might know, React Native apps are mostly written in JavaScript. You can write native code, and we try to make it easy to do so, but most of the time you shouldn't be required to. And your JS code will be bundled with the JavaScript part of React Native. That includes React.js and the React Native built-in modules and APIs. And it will be compiled to ECMAScript 5 using Babel. And then when you run your app, it will be executed by JavaScript Core. That's Apple's JavaScript virtual machine that's available by default on iOS and will be packaged with your app on Android. So Ide and Chirag already talked a little bit about how threading works in React Native. But when you launch your app, it starts running the main thread. And React Native will load your JavaScript code, and will start a new thread to run it. Moving it to a background thread allows us to reduce the contention in the main thread. That's where the native UI lives. And we try to keep it as available as possible to keep your app responsive. So React will then render your components on JavaScript. And these will generate a bunch of native view operations to be executed. So these view operations, such as create, update, and delete, will also be executed in a separate thread that we often call as a shadow thread. We call it that way because it only has the shadow nodes that are basically basic objects that only have the necessary information to calculate the layout. So it's basically just doing the math to know where it should render your component. So after that, all the native views will be created and rendered, and that's when you can actually see your app on the screen. So if you note at the bottom, there's also a block with native modules written with a bunch of threads coming off it. So on iOS, every native module will have its own thread pool by default. And on Android, all the native modules will share the same thread pool. But the point here is that all the native modules work is done off the 3 main threads that we have now. So that's about all I wanted to know to talk about architecture. And let's talk about performance. So our goal was to improve React Native's performance. But in order to do so, we have to be able to measure it in the first place. If we start working on optimizing anything without having proper data, we'll have to guess what's the bottleneck. And there's a good chance that we'll guess it wrong. So in the best case scenario, we'll end up with a premature optimization, which, as Kenneth already said, premature optimization is the root of all evil. And in the worst case scenario, we might actually end up hurting the performance. Since if you don't have how to assess what's the impact of our changes, we won't be able to tell if it was good or not, or unless it's something very major that we can actually feel by just using the app. So to illustrate that, I just wrote a sample app that I'll show how to identify the bottlenecks and evaluate the optimizations we make. So this is a very small feed in which we're hiding some languages, some words that are actually programming languages. So let's take a look at what the app looks like when it's running. So it takes a while to start up, and you notice that when we scroll, it lags because it's taking too long to render each post. So that doesn't give us that really smooth feeling and experience that we're looking for. So let's see some of the tools that we can use to investigate these issues. So there are 3 tools that I'm going to talk about today, and some of them are only available on iOS right now, but we are working on making them more consistent across platforms. The first one is the Perf Monitor. It's a small overlay that works in-app that gives you some quick and lightweight insight into how your application is behaving. The second one is Systrace. So Systrace is available by default on Android, and we have implemented something very similar on iOS. It's a marker-based profiler, and it's very good to give you some macro-level overview of how the application is behaving across native and JavaScript. And the last one is the CPU profiler. This is a JavaScript profiler that's actually built into JavaScript core, but currently it's not exposed anywhere. So we added some hooks to allow you to have fine-grained profiling in your React Native app. So let's take a look at the Perf Monitor first. So it's this overlay, as I said, and you can drag it around, and it has up to 5 views. The JavaScript core one might be hidden if it's not available at the runtime. And the first one shows the resident memory. That's the current amount of memory that's allocated to your process. And it will grow as you allocate more memory. The second one is the size of the JavaScript core heap. And it shows how much memory your JavaScript is using. This will only be updated once a garbage collection happens due to some limitations in the API, but it should give you some insight. The third one is the view count, and it has 2 numbers. The bottom one is the number of views your application currently has, and the second one is the number of views that are currently on screen. So the bottom number will often be bigger due to views that can be optimized out, so nested text, such as nested text, that can be merged, and views that are off screen that can be optimized out. After that, we have 2 graphs. The first one is the main thread FPS, and it will update every second and will tell you how many frames did you manage to render in the previous second. So we aim to keep it at 6 FPS as long as possible. That's like as far as it's the frame rate of most of the current phones, so it's as good as it can be. The other one is the JS FPS. And even though we are not actually rendering from the JS thread, the updates are still driven from JS since they come from React. So frame drops in this thread will likely affect your app's responsiveness. So the next thing that it gives you is that it might be helpful is that if it's available, it will print the garbage collection logs to Xcode, so you can know if we're generating too much garbage. So let's see how we would use the Perf Monitor in the sample app. So you shake the device, you show the dev menu. You shake the device, you show the dev menu, you show the Perf Monitor, and then you just use the app. And as we scroll, you'll notice that the JS frames goes like super down. So it shows that something is slow in JS, but it doesn't give us much. So usually from here, just use Systrace to have a look at what's the overall system state. So before I said that Systrace is a marker-based profiler, but what does it mean? It means that we have to explicitly add some code to the app in order to have information show up in Systrace. But React Native already has a reasonable set of markers by default that will include markers on sensitive bridge operations, such as JavaScript loading and execution. It will automatically inject markers on all the native modules, both the built-in modules and the ones that you write. It also has markers around React lifecycle methods, such as render and mount. But in case you want to see more than Systrace is showing you, you can actually manually add markers to your code. So this is the API. I know it's disturbing that the first methods doesn't match the case of the other ones. but it's actually a macro. It has some special behavior due to perf reasons to reduce overhead, so it's intentional. So there are just 4 methods. The first one is for synchronous operations, and it has to start and stop in the same thread. It will show up as a simple block in the output graph. And the next one is asynchronous events. Those allow us to start and stop in different threads, and will show as the same blocks. You can specify the thread to group them. And yes, the next are flow events. They are just arrows that show in the graph that are helpful to indicate how our computations are flowing from one thread to the other. Immediate events are the ones that don't really have a duration, such as a vsync or a garbage collection, for example, and will be an almost invisible tick in the graph. And you can also add markers from JS. But right now, we currently expose sync and async events, and they have a limited signature that just takes the profile name that will label the block in the final graph. So to capture a trace, the process is pretty similar to using the perf monitor. You just bring up the dev menu by shaking the device, you press start systrace, and you interact with the app. In this case, we just scroll. Then you shake again, and you stop systrace. Once you stop it, it should automatically open the trace in your browser, and should look something like this. So it's a lot of information. But if you look at the left side, it's all grouped by the threads that you have. And the blocks are created with the APIs I described before. And systrace is really nice if you want to understand what's happening in your app. So you see what's running in which thread and what started it if you look at the flows. And it can also be helpful to identify bottlenecks. So mostly you can find architecture bottlenecks because it's not super fine-grained. But you can easily identify if something's wrong, like these massive blocks on JavaScript. So if we zoom in that zone, in one of those massive stacks, we'll see that they last many frames. Like these vertical stripes are the frame boundaries. And if we look at the middle of the stack, we can see that there's a call to update component list view, which means that we are updating the list view. But the culprit is actually at the very bottom. It's a call to render a static render component. So this doesn't give us much. Like static render could be anything. It's like it's built into React. In an app this size, where we basically just have a single component, we could probably just look around and find what's wrong by tweaking the methods. But let's not guess and see how we can find with like 100% sure what's the bottleneck. So for that, we use the CPU profiler. In order to use the CPU profiler, you have to compile a separate dynamic library for the target iOS version. It should be easier than it sounds. We provide a makefile with React Native. You can run like a one-line command, and it will build this dynamic library. And after that, you can just rerun your app, and it will automatically show up a new option in the menu. So you start profiling. The process for generating the profile is the same as with systrace. You can simply shake the device, start profiling, interact with the app, do what you want to profile, shake again and stop, and then you get a pop-up like that will give you the location to your profile and tell how you can load it to visualize with Chrome DevTools. So if you haven't seen it before, it looks kind of like that. And here we will use the bottom-up profile that will show us the most expensive leaves at the top. And here, the top one is anonymous functions, which doesn't give us much either. It takes 48% of the execution of the program, which is a massive amount. If we compare that the second one, it's 40%. That's the program. That's basically when it's executing top-level stuff or it's idle. So here's, but if we expand it, we can see all the callers of that anonymous functions and how much of the time was spent when called through that caller. So the number, almost 48% in the top one, is basically the amount of time that was spent in the anonymous function when it was called through for each. That doesn't give us much either. But if we keep expanding, now we can see a function that's part of the application code. It's called filter text. It takes 47.9 to 1% of the time. And the location, that's actually in the index file of the sample app. We can take a look at the implementation. Here's what it looks like. It's not the best piece of code I've written, I have to admit. It takes a time proportional to the number of languages you have times the length of the text squared. But we can speed it up by making it slightly shorter. We just create a regex of the words, and it should be much better. And here's what it looks like afterwards. So it starts up much faster. I scroll as fast as I can, and it's pretty OK. So let's talk about, now that you've seen how to optimize it, let's see what we've done to optimize React Native. I'll split it in two parts. So product optimization, that's basically what we've done to optimize our products, and hopefully it can give us some insights on how to optimize your own React Native products. And some core optimizations that are things that we've changed in the framework itself to make React Native faster. So product optimization first. And the nicest part about product optimizations is that and it's something that you should keep in mind, is that React Native apps are, before anything else, React apps. So most of the optimizations that we do to products are the same that you would do to a web React app. So the first one is components keys. If you have a list in React, if you have a list in React and you don't put keys in your components, you get a warning saying that you should add it. That allows React to identify when you move items. So if you have a huge list and you remove the first item and you are just using array keys as the indexes, React will just delete the last component and re-render the whole thing. We had issues internally with a video product. As you might have heard in Steve's talk, playing video is super expensive because we have to re-render many times a second, hopefully 6 times a second if we have very good perf. So I started investigating and I ran a C-trace, and it looked kind of like that. It's OK, but you have nothing to compare with, so we don't know what it should like. We just know that it's not good because you use the app and it feels bad. So I compared with the older version, and if you look at the JavaScript thread, it's basically the same thing. But the other 2 threads are doing much more work. If you look at the shadow thread at the top, and it's the second one at the bottom it's basically empty, and at the top, it's like a massive amount of work going on. And if we zoom in the main thread to see what's going on, I select the method so you can see the list at the bottom. Hopefully, it's a little bit small. But it's basically creating a lot of views, moving stuff, deleting stuff. So it's redoing the whole layout every frame when rendering a video. That just doesn't work. So where in the old one, if you compare, it was just changing the transform matrix of the video that should be super cheap. So it went all crazy, redoing the whole layout just because you picked your keys wrong. So it was a one-line change that got the product back from less than 10 FPS to 60 FPS. The next one is should component update. You can implement should component update to take control over React on whether your component should update or not. And if you don't implement it, React will always try to update your component. When you change the state of the component, it will traverse the whole subtree to check what's changed. But by implementing it, you can actually optimize your components, updating strategy, allowing React to skip that whole subtree. So sometimes you have a very expensive component that takes a lot of data, but you can simply compare the data based on an ID or something like that, and that's the base case scenario. You do a quick check instead of comparing a bunch of data, and the whole React reconciliation is much faster for that subtree. Sorry. The next one is the same idea of should component update. The easier way of making things faster is by doing less work. And quite often, we render more things than we need right away, which slows down the app. There was a great talk yesterday by Aditya, and people have been pushing this as a general concept in the web for a while. That's just send out whatever is necessary to start loading your app, and then progressively load the rest of the page. We can do something similar in React. We make the component render first only what's necessary, and add the rest of and update progressively, adding the rest of the content for that component. So this allows us to start with a much smaller subtree that will render much faster. And we've used this technique extensively on React Native products to improve the TTI, or time to interact. So next, let's talk about core optimizations. Apart from products, we've also been working on optimizing the framework itself, so every app is going to get faster. So some of the optimizations we've made include debatching. So if you watched the first talk about React Native when it was announced, you probably heard that React Native is completely async and batched. And to illustrate what that means, here's another C-Trace in case you liked it. So there's a lot of stuff going on. So if we break it down, we start with the initial script execution. That's when we inject your JavaScript into the VM. So it has to parse to generate the bytecode. It will execute the top-level functions your requires. It will set up the environment and all that stuff. After that, everything is ready. We can execute our application. That's basically render your top-level component that you registered when you create a React app. So these will basically just render, call like react.render. And after that, we can create all the shadow views, as I mentioned before. When we have all the shadow views, we can calculate the layout. Once we have the layout, we can finally create the native views. With the native views, we add all of them to the screen, and then it's when you can actually view your app. But do you notice something very bad about this graph? This is a dual-core phone, and we are only using one thread at a time. So it's no good if you have a lot of threads, but only one's running at each time. So if you look at the left side, that's the list of threads. Like there's a bunch of them, but it's only using one at a time. So because of all the batching, many of the parts of the system end up idle, waiting for its dependencies to finish. But the way that the bridge is implemented is that we call JavaScript with the action that has to be performed, and it returns a batch of native calls that were triggered during that execution. The only way to execute native side effects is to return that from the entry point function. After that, there's no more JavaScript running. You already returned. The thread is idle. So it turns out that we can actually have synchronous functions in JavaScript core that allow us to call back to native during the execution, from the middle of the JavaScript execution. So they're not part of React Native public APIs, and that's a design decision, because it would be pretty bad to execute anything expensive, synchronous, while you're running your JavaScript. But still, we could leverage it as an optional optimization to the framework itself. We provide a function that allows JS to report partial progress, and the framework will use it if it's available. But when running in different environments, such as like debugging in Chrome, it will just fall back to the original behavior. So after that is what it looks like. If we look at the shadow thread, the shadow view creation now is spread all along the React render. And we can see that now we are using 2 threads at a time. That's a little bit better. But the React Native render part at the bottom is still a massive block that's waiting at the end, which takes me to the next logical optimization. That's incremental UI updates. So it would be great if we could also create the views as soon as we create the shadow views, so we wouldn't accumulate so much work at the end of the batch. Well, it turns out that we can just do it, and here's what it looks like. So if we label it again, we can see that now, as soon as we have the JavaScript running to render our application, we start creating the shadow views, and basically at the same time, we also start creating the native views. So now you can benefit much more from the multi-core processors that most of the phones have nowadays. And as a result, if we compare the amount of time that we spent that was blocking the main thread during the native UI render, it's much smaller. So all that huge frame is like the app was not responsive anymore. So with that in mind, it sounds like debatching all the things is just the way to go. Let's not do anything batched anymore. But that's not how it works. Turns out that the next optimization is actually batching cache requests. Yeah. So I was looking for the next thing we could make faster. And my usual workflow is that I run a C-Trace. I stare at it until I find something that doesn't look right. So I ran, and I saw that. It's like, OK, maybe we debatched something that we shouldn't. And if you look at that, they're all coming from the thread that's called async local storage. That's where the cache lives. So we were just doing requesting one key from the graph at a time from the cache. So I figured out, well, maybe that should be batched after all. And now we can't even see anymore, but there's a tiny arrow in red. Which brings me to my conclusion. Don't assume. Profile. That's it. Thank you.
All right. So this is our last full 30-minute talk of the conference, and it's going to be Andrew Clark. So probably a lot of you know him as ACD Lite. He has a lot of popular open source projects. Flummox, I guess, is now gone, but Redux Router, Recompose, Realm, Flux Standard Actions, and Redux Standard Actions. He's also a contributor to Redux. He spent a lot of time exploring post-React architectures, and so he's going to share some of what he's learned with us today. I just want to point out, though, that on Sunday his car was broken into and his laptop was stolen with all of his slides on it, and since then he's been working nonstop to remake them. He hasn't complained even once about it. He's just like really nice, great guy. So let's give him a big round of applause as he comes in.
Hello. Yeah, so you know a talk is going to be really great when you have to start it out with basically the dog ate my homework. But it did happen. I finished my slides like 5 minutes ago, so we'll see how this goes. I'm excited to see how this presentation is. I hope it's good. So hi, my name is Andrew Clark. I'm an engineer at OpenGov. Today I want to talk to you about what I want to call post-React UI architectures. I also thought about calling this like React adjacent architectures because they're not really in the post-React era, I guess. It's more just they came after React. They take inspiration from some of React's core ideas, but diverge or move beyond them in some key ways. So to frame this, why do this? Why is this a useful exercise? You've probably noticed a theme throughout much of this conference of looking to other libraries and frameworks for inspiration. We've had a few really good talks about this so far. The React ecosystem has been shameless in stealing from other communities, and I mean that as a good thing, obviously. So on an individual level, the reason it's good is that it makes us better engineers. You've heard that today. And if you're like me, you often hear people say things like, React made me a better JavaScript developer. Well, similarly, learning about React alternatives is going to make you a better React developer. And on a community level, it pushes us forward and leads us to some really cool projects, like Redux. Another goal of this talk, and this is another theme that we've discussed particularly today, is to serve as kind of a high-level intro to functional programming. Many of these post-React or React-adjacent libraries and frameworks, like React itself, follow some FP principles. Functional programming is something that many of us have become interested in since using React. I know it's especially true for me. But if your experience is mostly in imperative-style programming, as mine is and was, learning about it can be pretty overwhelming. You're bombarded with all these new concepts, strange, incomprehensible syntax that makes no sense, and mathematical-sounding jargon. You know, monads and all that garbage. So for this talk, I'm going to try and skip the jargon, because I barely understand it myself, and I'm going to spare you any new syntax and attempt to present these concepts in terms that will be relatable for a React developer. And so, in fact, all the code I'm going to show you today is in JavaScript and React. The frameworks I'm going to focus on are Elm, and specifically the Elm architecture. Less so the language itself, which Jameson did a really good job giving you like a high-level overview of it. And Cycle, which many of you have probably heard of. It's a data flow library that's based on observables. By the way, I also originally wanted to cover Ohm. I think that's in the talk description. I had to cut it for time, but it's really cool. Don't mean to suggest that it's any less interesting than these other frameworks, just the limits of the format. But fortunately, we heard about that earlier too. But ultimately, the title of this talk is Back to React for a reason. This is really a talk about React and how to make our applications better by stealing shamelessly from other libraries. and frameworks. So hopefully in the process we can learn more about what makes React special at the same times. So in that spirit, before we get into Elm Recycle, I want to talk a little bit about React components. Often in blog posts and talks at this conference, we've seen a few versions of this, you'll see a formula that looks like this. This is essentially saying views are a function of data, or React components are a function of data. This is an elegant formulation that communicates some key things about React, that it's declarative, and that it's all about inputs and outputs. But while the formula is useful, it's not strictly true, right? Because it implies that React components are pure functions. If that were true, then the only way to update your view, to update your app, would be to give a component new data. And when we say data, we mean props in this context, right? Because props are the thing you give to a component. Yet, as we know, components have the ability to update themselves. They can have local state. In other words, you can say that they have side effects. They can communicate directly with the outside world. So this is an important distinction versus a framework like Elm, whose views literally are pure functions and rely on a separate system for managing effects and updates. So if we're going to compare functional inspired UI architectures, state is an important topic because it's an important topic in functional programming, and it relates to this idea of purity versus impurity. We've also discussed this at this conference. Purity is desirable for reasons that are likely familiar to all of you. They're predictable, they're testable, they're declarative, they're good for if you run, they're easily parallelizable. So generally the goal is to maximize the pure part of your program and minimize the impure part. Impure code, of course, is necessary to communicate with the outside world, of course, e.g. via events like button clicks or keyboard events. So functional programs have to be rigorous in how they coordinate between the impure and the pure part. So one way to think about this is that new information in a program, think mouse events, keyboard events, gestures, etc., is always impure by definition since it comes from the outside world. Before it can be used by the pure part of our application, which is hopefully most of the code that we write, it somehow has to be purified. This is an imperfect analogy, and I just made it up like 2 minutes ago, so it might not make any sense, but events are kind of like crude oil, right? And you have to refine it before you put it into your car, which is our app. So yeah, lame analogy, but let's take a look at how this idea of pure versus impure applies to each framework. In React, we already mentioned that functional components are pure, but the pure versus impure distinction happens in class components as well. So if we look at an example class component, and I just kind of stole this from the React main docs page, like the README, the docs. If we look at this example, it's clear that there's some impure stuff going on here because we're using setInterval and we're attaching it to the instance. But if you kind of squint, there's a part here that is a little bit pure. You can think of it as pure, and that is the render method. You're thrown off a little bit by that this.state.seconds. It's accessing local state, but conceptually we can think of render as a pure function for a given set of props and state. And this is actually one of the first things we learn as React developers, right? Is to keep side effects out of render and just simply output a view using the current props and state. So I've done this thing that I'll do for each framework where we have these 3 columns. So in React, the impure part is setState and the lifecycle methods. The pure part, quote unquote, is the render method. And then we have this thing in between that has to coordinate between the pure and the impure part. And in React, that's like when you pass props, right? Because all state in React is local to the component. And that keeps our components isolated and maintainable. So when you pass a prop to a child component, it doesn't know if that's coming from state or anything else. It just knows it's a prop. So let's compare this to Cycle. Cycle doesn't have an imperative API like setState. Instead, it describes data flow using an asynchronous primitive called observables. Observables are streams of data. They represent values that change over time. They're often conflated with events because you can subscribe to them. But the thing that makes observables special is that you can apply composable stream transformation to them. You shouldn't be making lots of subscriptions. That's a mistake I made when I first was trying to learn about them. So these composable stream transformations are very important. For instance, and I apologize if I was unsure if I wanted to put this slide up here. This is from a really cool website called RxMarbles, which you may have heard of. Hopefully this makes sense. On the top, you have a stream of values spread out over time. The line represents time. And in the middle, you have the transformation we're applying to it. And on the bottom, you have the resulting stream, again, spread out over time. So this one, hopefully, you can decipher. We're taking an original stream, and we're filtering any of the values that are not over 10, essentially. So here's another example. This is map. This is just, it's like any other mapping function, except you're doing it over a sequence and not just a single value. We're just multiplying it by 10. Here's another one, scan. This should look a little bit familiar. Scan is like reduce. For each value, where represents the sum of all of the values in the sequence up to that point. So if you're familiar with Redux, this is a good way to implement a Redux-style data flow in observables. So the key thing to understand about these transformations, and there's a lot more examples online, rxmarbles.com, I think it is. The key is that when you apply a transformation to a stream, you're not changing the original stream. You're creating a new derived stream. This means you can express complex data flows without lots of subscriptions. In fact, many apps only have a single subscription, and it's handled by the framework, not in your actual user code. So here's, again, I ripped this off straight from the Cycle website. Here's a diagram of how data flow generally works in Cycle. On the top, we have our application, a function called main, which is essentially just one big stream transformer. Remember, streams and observables are synonymous here. It's a function that takes in input streams called sources and outputs streams called sinks. Again, when you transform a stream, you're not actually modifying the original stream. You're just creating a new stream that's derived from the original one. On the bottom, we have these things called drivers. These are a really clever abstraction for dealing with side effects, and this is the part that communicates with the outside world. All communication with the outside world has to go inside of a driver. Drivers provide the sources for our apps, and they receive the sinks. So as you can see, this is like a unidirectional data flow, just like in Flux or React, similar concept. So in case this doesn't make sense, let's walk through the most common driver, which will be the most relatable to a React audience, perhaps, which is the DOM driver. That's that top one in the drivers section down there. The DOM driver listens for user events like button clicks, keyboard presses, etc., and passes them into your main function, into your application code. Your application applies transformations to those events to produce an output stream of virtual DOM elements. And then that stream of elements is returned back to the DOM driver as a sink, which takes that DOM representation and mutates the actual DOM using the virtual DOM representation. So that should sound pretty familiar. And there are other types of drivers, including ones for HTTP requests, for interacting with the history API. There's even an experimental driver for React Native. You could even just use normal React. Most people don't. They use the virtual DOM driver. But there's nothing stopping you, because this is really just a data flow abstraction. It's not anything that's tied to any particular kind of view primitive. So drivers are a fairly neat, flexible abstraction that solves this pure versus impure problem in an interesting way. So let's plug this into our chart. On the left, you have drivers, which are impure. The pure part is your main function, which is it's one big stream transformer that's composed of some smaller parts of your app. And then the in-between thing that I'm calling it are your sources and your sinks. Arguably, maybe the drivers are in between. I don't know. This isn't perfect, but the idea is you have something that's coordinating between the pure part of your code and the impure part. Oh, wait, let me go back. So in a real Cycle app, you'll actually have multiple of these data flow components like that. That's the data flow component. You're going to have multiple of those data flow components that follow that diagram, which compose together into a single program. I don't have time to go into the details of that, but it's conceptually similar to how the Elm architecture works, which we are going to discuss here in a bit. So some of the high-level benefits of the cycle architecture are, observables are a good abstraction, arguably. There's some controversy, but good abstraction for expressing complex asynchronous logic using stream transformations. It's highly declarative, so your application code is written using pure functions. And drivers are a nice abstraction for dealing with impure code. It allows the bulk of the code that you write to be nice and predictable and pure and testable and all that good stuff. So surely this is way different than how React works, right? Well, yes and no, I would say. The update cycle is different in React, but I think there may be something to the idea of components as essentially stream transformers. So let's explore that idea real quick. Let's go back to our formula. We discussed why this formula isn't complete because it doesn't express how updates work. When you render a React component, it doesn't just return a single unchanging view. If the component is stateful, like that timer component we were looking at earlier, it's going to return many views over time. In the timer example, every single second. It's going to render a new string. So let's think about how we can adapt this formula slightly to accommodate this idea of returning multiple views over time. So this isn't jQuery, this is a convention, don't worry, this is a convention that Cycle uses to indicate that something is a stream. So now what we have here is we're saying a component is a function of data that returns a stream of views. And this description is a bit closer, perhaps, to how React components work. But the right-hand side is still maybe not quite right. Because when you mount a component, it's not just receiving a single set of props over its entire life cycle. It's going to receive multiple sets of props before it eventually unmounts. And because components may accumulate state over time, the 7th render of a component isn't necessarily going to return the same output as the 17th render. So let's think about this. The nth render of a function is not a function of a single set of props, it's a function of a sequence of props. All of the props that have ever been sent to that component over time. So let's update this one more time. Oh, sorry, I forgot to advance, but that's just what I just said. Okay, so now we have the data. Again, this is props, these props, and when we're talking about React. Now we say that a component is a function that transforms a stream of data or props into a stream of views. So notice how our updated function f is now very similar to the main function that we were looking at in that Elm diagram. It's a stream transformer. So this isn't perfect still, like it's not an ideal, still not an ideal description of how React components work, but, and it also doesn't cover all of the surface area of the React component API, but as it turns out, the idea of a React component as essentially a stream transformer actually works pretty well, and I can prove this by giving you this example. So let's say we have a component called, or a function, a helper, called createComponent, and it accepts a single parameter, and that is a function in the form of f that we just saw on the previous slide, which is a function that takes a stream of props from the owner and emits a stream of React elements, which we're just going to call vdom here. So when you pass this function to createComponent, it's going to return just a regular old React component that you can render just like any other. So for instance, here's how we would implement that class timer that we saw earlier. Functionally, it's the exact same thing as that class component, but you can see we're using this createComponent helper that we just imagined. If you can't read this, I'll step through it a little bit. Observable.interval, basically, it's an RxJS function or helper. It creates an observable that emits a new value every second. Scan, is we talked about that. That's just essentially adding 1 to n every single second, so that the value at any time is the number of things that have been emitted from the source. And then at the end, we just map that accumulated value to some React elements. Very simple div there. And there you go. It outputs this thing here. So the same exact, I'm not going to scroll all the way. That's not valuable. So it's the same exact thing as that class component we saw earlier, but arguably, It's a little bit easier to track the data flow in this at least if you're used to observables. I realize that if you're not, this might not make any sense, but hopefully it does. Here's another slightly more complex example. I stole this idea from the Elm architecture tutorial, which has a similar thing. So this is just fetching random GIFs from, is it GIFs or GIFs? Half of you are going to say I'm wrong. So I'm going to say GIF. This fetches a random GIF from Giphy, whenever you update the input. And does some other special things, like it's going to debounce whenever it fetches, so that it doesn't fetch on every single key press. This distinct until change is a nice helper in RxJS that just will skip over values that are equivalent to the previous value, which is important so that if you have a re-render and the same exact prop is sent to you, even if it hasn't changed, it doesn't try and fetch again. And then we already know about map. So hopefully you can follow this. We're essentially just taking the topic from the prop stream. So this time we actually are using that source prop stream. There's this thing called flat map, which if you don't understand that, don't worry. It's getting a promise and it's flattening it back into the stream. And then it maps that to some React elements like we did last time. So if this were my original talk, I would compare this to the class component version of this. But you can imagine that if we were doing this as a normal class, it's not going to be this expressive. You're going to have to deal with some weird set state stuff. You're going to have to use a debounce function, and it's going to be a little bit more complicated. So for these asynchronous operations, arguably, observables are a nice way to do that type of stuff. And what is essentially 7, I can't count, 7 lines? So observables in React can be a nice pattern. It's not great for everything. For example, if you need to mess with the DOM directly, probably should just use a class. And it's not as pure of an abstraction as Cycle, but React's API is designed in such a way that it makes experiments like this really easy to implement. So in case you think that create component thing was a terrible hack and with lots of really gross code underneath the hood, it's actually fewer than 50 lines long, and it's pretty straightforward. It's just using component will receive props. And it's also not fully reactive the way that you could argue that Cycle is fully reactive, because React is still controlling the flow of props across components. We're not actually taking control of all of the data flow. We're just the data flow inside of a component, in between when it receives props and when it actually renders. So next, let's talk about the Elm architecture. So again, Jameson had a really good talk about Elm the language. We're going to talk about the Elm architecture, which maybe you have not heard of. So in an Elm application, as in Cycle, your app is essentially made of these really big monolithic functions. But unlike Cycle, rather than operating on streams of values, Elm applications operate on discrete values, so there's no notion of time the way in observables have the notion of time. Streams do exist in Elm. They're called signals, not exactly the same thing as observables, but they're similar in spirit. If you understand one, you can probably understand the other. But in the Elm architecture, they're mostly in implementation detail. You can really make fairly complex apps in Elm without knowing what the hell a signal is at all. So we've talked about how Elm views are pure functions, which means that they can't have imperative APIs like setState. So if they can't use setState and they don't operate on streams like Cycle, and everything has to be pure, how do we model local state in Elm? So the way it works is every component in Elm exports not only a view, but also an update function. And update functions are functions that take the current state and an action and compute a new state using that. So maybe this sounds familiar. That's because update functions in Elm are exactly like reducers. The Elm architecture is basically Redux, but for components. It's probably more accurate to say that Redux is a subset of the Elm architecture, not vice versa, just to be clear. So where Redux is concerned primarily with application level state, so state that's important to your entire application usually. For instance, if you think about the way a lot of people use Redux, which is to do data fetching, if you fetch a bunch of posts, that's state that your entire application might care about, or at least one or more components might care about. But Elm is concerned with local state. It's more comparable to as a replacement for the set state API at the component level. So Elm apps are essentially made from two big functions: a big update reducer composed of smaller reducers, and a big view composed of smaller views. So you can imagine that the view composition works pretty similarly to any other kind of function composition, or the way that you compose stateless functions in React, except you don't have this intermediate thing like a React element. It's just a function that returns a description of some virtual DOM. So when an event happens in Elm, it is turned into an action and sent through that big, giant monolithic reducer to calculate a new state tree. And like Redux, the state tree is just a single immutable value. Then the new state, or model, as they call it in Elm, is sent to the giant view, the big composed view, to generate a new virtual DOM description. Because Elm apps are made of these gigantic monolithic functions, updates always happen from the top. So this requires a bit of cleverness in how we design our component modules. The key to the Elm architecture is the actions inside actions pattern. It's a bit hard to explain unless you've actually done it or seen it. I probably looked at it, I've read through the docs like several times before I truly understood it. And it wasn't until after like Redux was a thing that it clicked like some sort of weird reverse inception. That we had essentially been doing the same thing in Redux as Elm had been doing the whole time. By the way, this is the part of the talk that would benefit from a really nice animation, which I promise you my original presentation totally had the coolest animation. When a component in Elm dispatches an action, but it's not called dispatch, by the way, in Elm, but I'm going to describe this in terms of JavaScript. It's actually dispatching a nested action that looks kind of like this. So you have this meta action with a type, and then you have a payload, which is just another nested action inside of it. So the parent component is responsible for unwrapping that inner action and calling the corresponding update function. So the second part of this is we don't want the inner function to have to think about nesting actions. It shouldn't be aware of its owner at all. So we don't want to actually construct these weird nested, and imagine there's like more than 2 levels, it's going to be even bigger than that. Yeah, we don't want to have to worry about that. So we give that responsibility to the owner. Before the owner passes the dispatch prop down to the child component, it's going to wrap that dispatch, kind of like an enhancer, if you remember that. It's going to wrap that dispatch function or method in something like this, so that when the action is dispatched, it's actually being dispatched inside of a meta action. This way the child thinks it's dispatching normal actions even though it's dispatching this bigger thing. There we go. So here's an example of what this might look like in JavaScript and React. So at the top you have this init thing. It's kind of like get initial state. In this case, we're just keeping track of a string, so it's pretty straightforward. It might be, another component would probably be like an object or a record. Update is a reducer, so I don't have to explain that to you. This is a view. This is the third part of an Elm component, is the view. This is just a React component in the way that we're implementing this. It's going to receive 2 special props, model and dispatch. Model is just the state that corresponds to that component, and dispatch is like dispatch in Redux. And so then this is pretty naively implemented, but as the event handlers for the input and the button, we're just going to dispatch an action when those events fire, and that will, by the framework, be handled. We'll send the action to update, calculate a new model, and then re-render. So at the bottom there, on the final line, we see this function called start. So that's kind of like that create component function that we saw earlier when we were talking about RxJS. Just imagine it's a function that exists that takes these 3 Elm-style modules and turns them into a normal React component. Again, it's just a React component, so you can render it in any context whatsoever, and the consuming owner component does not have to have any clue that you were transgressing by using this stupid architecture. So here's an example of this nested pattern. So this is the same component we were looking at earlier, except I forgot to mention that the actual inputs, those input boxes, are using this Elm style pattern. The reason I did it this way is that you'll notice that we have a mixture of two different architectures here. Not only are we using React, we're also using the Elm architecture to do that input box, and we're using that RxJS cycle architecture to do the GIF fetching, and neither of them has to know about what the other one's doing, because they're both just React components. So that was the idea I was trying to communicate there. And then the other idea you want to look at here is that we have two instances of this Elm-style component that are, and by the way, this is just exactly what we're looking at here, is that we have, I realized I forgot to kind of walk through that, but we have, sorry. Oh, I screwed up that slide. See, this is what happens when you when you make the presentation 2 minutes before you give it. So in the model, essentially, we're storing the, I apologize. Basically, in the model, and I'm going to post this online, so you can play with it yourself and don't have to watch me stumble. But basically, in the model, we're storing two models. We're nesting two models inside of it. And then we're passing those models down as props. So screwed up the slide, but hopefully when you look at it online, if you ever do, it will make more sense. So yes, this essentially lets us keep all of our state in one big object, and even though, and while still maintaining this isolated property, so each component doesn't have to be aware of the other components. Also notice that, and this scales fairly well. Also notice that there are no selectors here. That's one advantage. You don't have to have selectors because everything is just co-located with the view that they are interested in. Again, this works for component state pretty well. It wouldn't work if you were trying to do more like application level state. It'd be a little bit more complicated. So some disadvantages, you'll notice that there's a lot of ceremony involved in doing that nested action inside of actions pattern. And since JavaScript lacks features like strong types and pattern matching, it makes Elm's strictness about things like side effects harder to stomach. Another disadvantage is that because updates always occur from the top, you have to be really careful about performance. In React, you can mostly take performance for granted because when a component calls setState, it's only updating that component and all of its descendants. But when you render from the top all the time, you have to have a way to cut off subtrees from re-rendering. Elm does this using a function called lazy, and there's a few functions called lazy, which works pretty much just like the pure render mix in React. It implements should component update, and it returns false if all of the props are referentially equal, or just equal in the case of Elm. It's not impossible to do this if you use the Elm architecture in React. Like I said, you can just use should component update, but it is another extra thing that you have to be really careful about. That being said, there's still some benefits, and they're the same benefits that you have with Redux. Reducers are really easy to test. Whiz-bang features like hot module replacement and time travel are pretty straightforward. And this is also the part where you pretend that I implemented that here. Serialization is very easy, again, because it's just one big object. Also, we already have so many cool Redux extensions out there that if you wanted to, all of those are easily portable to a system like this. In fact, this is where you imagine that I had a Redux DevTools example running on that GIF component, which I totally did in my original, I promise, in my original presentation. By the way, also I should mention that the Redux DevTools themselves implement this nested actions inside of actions pattern. It's essentially the Elm architecture, which is pretty cool. So if you ever want to look at how the Redux DevTools are architected and also gain a little bit more insight into the origins of Redux, because the DevTools really drove a lot of the initial design of Redux, that'd be a good homework assignment. So you may find that certain components do lend themselves to this Elm architecture. Just be aware of the trade-offs. And again, we have this chart. The impure part of Elm is again, like these aren't perfect columns, but you call out to JavaScript whenever you want to do something impure. Usually you have these abstractions called ports, tasks, and effects, which I can't go into right now, but those are the in-betweeny things that coordinate between the pure part and the impure part. And the pure part, as I discussed, is the updates and the views. Wow, I am actually over time, shit. So what's the point of all this? I've shown you 2 new ways to start writing React components, but why should you care? Should you go back to work tomorrow and start using them? No, please don't do that. For the most part, you should just keep writing your components the normal way. It's proven, it's stable, there's an entire community behind it, and most of the time it just works. But you may find there are specific areas of your app that benefit from these alternative approaches. So at OpenGov, we write lots of React code, and most of it is fairly standard stuff. But there are a few areas where we deal heavily with asynchronous logic, or we have state management concerns that are complex enough that set state just doesn't cut it. So in those cases, sometimes we use observables, like I showed you, or sometimes we use the Elm architecture. In fact, I have a component that I was just working on a few weeks ago that uses the Elm architecture, and it uses that RxJS thing I was showing you, and it uses Relay, and there's even a little bit of Redux in there. And that sounds ridiculous, but it actually works pretty well. When we keep it nice and maintainable by using higher order components to kind of split up the separate pieces of logic. And it's actually, believe it or not, more maintainable than the original version that just uses classes. So at the end of the day, blah, 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 I'll skip over that part because I'm over. We're just writing React components. So the point here is not to get you to use any particular pattern or library. It's to stimulate your curiosity for how these alternative systems work. Is to get you thinking about how to take full advantage of React's powerful component module, and is to encourage you to experiment with or steal ideas from other frameworks and bring them back to React. Thank you.
Okay, let's give him another round of applause, because that's amazing. Like, first conference talk that he's ever done, and his slides were stolen a couple days ago. Like, who steals slides? Why would you even do it? What are you going to do with it? You're going to do it, give it another conference? Doesn't make any sense. I guess you could use a computer for something, but whatever. All right, so anyways, this is sad because it's the last group of talks, but that's how it goes. Yeah. No. Thanks everyone for being such a great audience so far. We just have these 5 lightning talks left. They're really great, and hopefully, because they're so rapid fire, you won't be too tired because we've kept you for this hour and a half period of time. So first up, we have Eli Rottenberg. Yeah, come on, Eli.
Hi. So my name is Eli Rottenberg, and my talk is about protecting your DOM from tampering using cryptographic tree transforms. So here's a problem I'm trying to solve. On the web, third-party scripts can violate the invariance of React. And they do this by mutating the DOM behind our back. This can be caused by invasive ads, buggy external scripts, or browser's extensions such as ad blockers. All these sources can access the DOM directly by working the document object using document.querySelector and document.querySelector role, or injecting style tags with new CSS rules or whatever. When they start doing that, bad things happen. You can have performance issues, for example, when they cause layout thrashing. You can have layout issues when new HTML nodes are inserted in a place where you didn't expect them. And of course, you have functionality issues when your app or website start behaving in a way it wasn't meant for. This is bad because we program our apps and websites to have a certain well-defined and predictable behavior. The whole point of using React in the first place is to have our apps and websites behave exactly how we describe them to behave. We do not want this to be compromised by external scripts. So here's a simple example of how a third-party style sheet would prevent a div from appearing. On the left, we have a snippet of JSX appearing somewhere in our app. On the right, we have an external style sheet injected by an ad-blocking browser extension. It targets a specific part of our DOM and hides it. This could break our layout, our features, or simply starve our business to death. Since we don't want this to happen, we can apply several transformations at the virtual DOM tree level to prevent these hacks from working. Our first transformation is class names obfuscation. It takes a component and transforms its render function so that all class names are replaced with an encrypted counterpart. This encrypted counterpart is not random, but it uses a one-way cryptographic hash function. So from the point of view of an external script or style sheet, it is as if it were random though. Static class names can no longer be used to target specific elements in our DOM. But this is not enough. The third-party style sheet could be modified not to rely on class names, but use tag names or CSS pseudo-classes. So that's where our second transformation kicks in. Tag names obfuscation. We use a similar technique, but this time tag names get encoded. Note that this does not require any custom component support or polyfill. Vanilla React supports using custom tag names like charm. Once again, we're using a cryptographic transform, so third-party scripts can't use tag names to target our DOM anymore. They would have to use quite complex selectors based entirely on the graph structure of the HTML tree, but with enough efforts, they could still manage to target it. And that's why we introduce our third transform, tree structure obfuscation. This transform is a bit more complicated. It inserts variable depths, intermediate elements to shuffle the tree structure itself, once again using a cryptographic hash, making it impossible to predict for third-party script. Now it is completely impossible for third-party selectors to target our DOM. So far, we have demonstrated how to obfuscate a single component. But for the transform to be effective, all components should be decorated. To do this, we use a simple yet powerful trick, which I think has many applications besides preventing ad blockers from working. We rewrite the render function of the root component so that the return element tree is transformed using the transformation I've just described. But then we also rewrite the render function of the components appearing in the return element tree exactly the same way. And this way, we have just defined a recursive tree transformation that will be automatically applied to all the components in the tree without having to manually decorate each one of them. So I've packaged these transforms into a small library called React Armor, which recursively applies all this transformation to all the components in your app. It obfuscates class names, tag names, and tree structure. The result is that no part of your DOM is targetable by static selectors. For obvious practical reasons, React Armor also allows you to apply the exact same translation to your style sheets so that you can keep using CSS to style your components while keeping your DOM safe from third-party mutations. Thanks for listening, and please feel free to check out the code on GitHub.
Hello. I'm Leland Richardson. I work on web infrastructure at Airbnb. I'm talking to you today about testing React components. First, let's talk about testing the UI. Before React, testing UI was hard. Once React came along, testing UI was possible, but for some reason, testing was still kind of hard. So, despite what Andrew Clark just said, we have our UI, and it's essentially a pure function of state. Oops. And pure functions should be easy to test. So what's making it so hard to test? One problem is scope. Testing leaf node components is fairly straightforward. The tests are nicely isolated. As we move up the tree, though, we're not only testing components at that level, but also all of the components in the levels below. So the answer is shallow rendering. And React has had the shallow renderer since 0.13. And what the shallow renderer does is it returns us the output of just a single component, regardless of how high up in the render tree it is. So what does this look like? The shallow renderer gives us what we want, a slice of the render tree, but we aren't provided with any tools to inspect it. As a result, we end up coupling our tests to our component implementation, rather than just the component behaviors we want to test. In order to fix this, I wrote a library called Enzyme. Enzyme exports a shallow function, which you pass a React element, and get out a jQuery-like wrapper that wraps around the resulting tree. Enzyme allows us to write the same tests that we had written before, but they're less coupled to our implementation. We can find nodes of a specific type in our tree by just passing in the constructor, or any CSS selector, or even an object that maps to props. Enzyme also allows you to easily simulate events and assert on state transitions. Enzyme exposes debug methods for you to easily figure out why your tests are failing. Tests are useful tools for telling us why something is wrong, but often it is difficult to understand why something is wrong. Logging your React render tree can often result in your terminal window exploding, but in this case, we just get nicely formatted JSX. In addition to shallow, Enzyme exports two other methods, mount and render, that do full DOM rendering and HTML rendering. They each return wrappers that are identical to the shallow API. So now we're wondering, what about React Native? We know how to test React components, but can we test React Native components? So if you try right now, testing React Native components is actually pretty hard for several reasons. So what's the solution? If you look around, there are lots of things on the internet that might tell you to mock it. So let's see what that might look like. So first we start off, React Native just uses React under the hood. So let's just give it React. But then, of course, React Native exports other things. Almost all of your views are going to have at least view and text. So we're going to mock that, and probably a style sheet as well. And then, of course, after you do more than a hello world example, you're going to have to use one of the other 38 component APIs and 35 non-component APIs that React has. And eventually, you're going to run into something that's a little bit difficult, and you're going to think, oh my gosh, is this really worth just getting one test to run? So the bottom line is, you should be spending your time writing tests, not mocks. So I've gone ahead and painstakingly mocked out the entire React Native API. It's all just plain JavaScript, so you can run your tests with any test runner you'd like. All you have to do is require the /mock entry file, and subsequent requires of React Native will be the mocked API. And with the mock loaded, you can shallow render and test your React Native components with Enzyme, just like you would with React. So where do we go from here? Integration testing is really useful, and I think it complements unit tests really well. Enzyme could be retrofitted with some of the popular integration test frameworks to make integration tests easier to write and more React aware. We can improve event simulation. Basic event simulation in Enzyme right now is supported, but doing complicated things such as drag and drop or typing is not easy to realistically simulate. Also, for React Native, this mock could get more and more sophisticated and better emulate a real device. Ideally, at some point down the road, we get to a point where the mock can be really thin and maybe even not needed. Thank you.
Where is the clicker? Oh. Morning. My name is Nikolai, and I work as a meta engineer at Automatic. You probably know us from our work for the WordPress open source project, and our main project is WordPress.com, which is a hosted service for building websites. It has a little bit more than 100 million users, and about 2 years ago, we decided to try and improve both the user and the developer experience, and we rewrote all of our admin interface on WordPress.com using JavaScript and our REST API, and the name of this project is Calypso. It was a monumental effort, but it was totally worth it because everybody enjoyed it. Both the users enjoyed the improved performance and reactiveness, and all of the developers really enjoyed building reusable components in the UI. Of course, it was all built on React using ES6, Webpack, Flux, recently Redux, and we have a lot of fun tech challenges ahead. Like we are trying to make it work offline. We want to do plugins, server-side rendering, but even though the tech party is really exciting today I want to talk about something else around Calypso. And this is that Calypso is 100% open source. We actually deploy directly from the public GitHub repo, and almost all of the conversations and all of the code reviews happen out in the public on GitHub. And we get this question very, very often, like why would you open source your main competitive advantage and your main product? And to be honest, given the ethos of our organization, this is not even the right question. Probably the better question for us is, why not? Why would we hide behind a private repository, and why? And especially given that a lot of the rest of our code is open source anyway. Of course, in addition to the philosophical advantages, there are a few more practical benefits too. Number 0, we have a lot happier developers. You know, open source is like the Golden Gate Bridge. It is very, very pretty, and everybody loves it, but very few people go there because it is very windy and chilly. And it's the same with developers. They don't write open source very, very, very often for various reasons. But now, a lot of our developers get to write all of their code out in the open in their daily work job, which of course makes for a really great GitHub pages for them later. Another benefit is that random people get to fix your random bugs. We have more than 100 PRs from non-automaticians, and even we get PRs like from people like the author of Lodash who just told us how to write loader stuff. Another good benefit is that Calypso is an example of a large open source single-page application. So if you need an example of a complex user interaction, totally go and look at our plugin updater. Or if you're writing an open source framework, Calypso can be a good test bed for you to show others that your framework scales. For example, Andre Stouts can probably rewrite pieces of Calypso in Cycle.js and convince the community that it scales. But to be honest, the biggest benefit for me is that we, by open sourcing Calypso, are sending a message to our team that it's okay. It's okay to take risks. It's okay to make mistakes, even if the whole world is watching. It's all okay. And by allowing ourselves this type of humility, and by allowing ourselves to be vulnerable, this actually makes us more open and makes us better developers. And if you trust psychological research, it even makes us better people. And this is the beauty of open source. Thank you.
All right. Hey, ballers. How we doing? Having a good time? You having a good time? Yeah, he's having a good time. All right, so my name is Gabe Scholes. I'm coming from Vancouver. I'm going to be talking about RxJS with React applications. Andrew Clark sort of already touched on this, but we're just going to get into a little bit more detail. And so in order to talk about this, we first need to talk about what an observable is, and I think the easiest way is to talk about it in the context of a promise, because they have a similar abstraction. And so with a promise, right, we know that this is a wrapper around a single asynchronous operation, and when it resolves, we can pass that along to all of our subscribers, but we can only ever do this one time. Well, an observable is just a wrapper around an asynchronous stream of values. So you can think of this as, like, say, an event handler or a WebSocket or a web worker or something like that. And so rather than just a single value, we pass on many values to all of our subscribers, and then at some point we say that we're done. Now, in addition to this, RxJS allows us to apply various transformations to observables. These transformations are immutable, so they always return a new observable, and like based on my little example here, you can see that they all follow from each other. So here we have like a click event observable, and every time those get passed down the chain, so you get this stream until you get a desired result. And finally, observables are also composable. So here we have 2 buttons, and every time we click on the top button, we're going to take that event and we're going to map it to a +1. And every time we click on the bottom button, we're going to map that to a -1. And then we're going to merge them together so that we have these 2 streams of +1s and -1s, and we're going to create a brand new stream of just +1s and -1s. It's a single stream. And then the last one, we're doing that reduce, where we keep a running count. And you'll notice that this reduce, this number that we're keeping track of, is without side effects. So here, it follows from the button clicks. So the button clicks directly affect. We're not dispatching some event. We're directly composing a stream in order to update the sum. And then so if you really want to understand the power of observables, here's an example that's a little bit more useful. So we start by tracking mouse events, but only when a mouse down event happens. And then we only want to take one of those events per second, and then only take them until a mouse up happens. So like this is a nightmare in vanilla JS, right? Don't even bother trying to do this. RxJS is like 4 lines. It's fantastic. Right, and so it turns out, RxJS and React, they pair pretty well together, I find. And so inside of our React component, we could use an observable, and we could use that to handle all of our event handling. And so at the top, we have this thing called a subject, and a subject is just an observable that exposes that push API, so being able to call next, but we expose that publicly. And then what we do, like the previous example, we click buttons, we push in +1s or -1s, and then we keep a running count. And then every time we get a new count, we just update, we call set state. But there's a problem with this. This is going to get a little bit sloppy because now React is not the only thing that is maintaining our state for us. If someone were to come along and insert a button called reset that automatically just calls set state and sets the count to 0, if I had pressed plus 20 times before that, and then I press reset, and then I press plus again, well, my total is now going to be 21. It's not going to be 1. So what we can do is we can take that observable behavior and pull it out of the component so that we get a pure component. So we just have a function. We're calling it clicker here. And what's important is what I've highlighted in blue there. And that's that count, the stream that we get from count, which is this running total. All of the behavior to describe this is right there. It's right in front of us. And if we really wanted to create that reset button, we would need to create an observable to maybe wrap this and then set the count to 0 or reset it to 0. So we have to directly do that. There are no side effects involved here. So yeah, should I use RxJS with React? I don't know. Like, there's a lot of considerations. Can come talk to me afterwards. I'm pretty sure I'm the only person at this conference wearing a dope fruit shirt. So one thing is like the learning curve, right? It's like pretty high. So you'll have to definitely take the time to learn it. It is very much worth it. Like totally changed the way that I've thought about writing JS. Totally recommend it. But it might be overkill, right? Like, why not just use vanilla event handlers in my code? A lot of the time, you get problems with your components because they're just too big. And making those set state calls all over like a 700-line component is a nightmare. Hopefully you do a good job of maintaining that, but we all don't, or some of us don't. So like 99% of the time, if you don't have this crazy observable streams that depend on each other, then vanilla JS is fine. Didn't really have a chance to talk about this. Andrew Clark sort of touched on this, but it is sometimes a good alternative to Redux. Cool story, Gabe. Thank you very much.
Hello. So, yeah, wrong side. Last 5 minutes of this awesome conference. I'm gonna talk about 6-year-olds learning React almost. So my name is Zach, and let's go back. My name is Zach, and I run a venture building company out of Morocco that's located somewhere in Africa. And so a couple of months ago, I was at my uncle's house, and his 2-year-old came and took away my iPad and started swiping the screens until he found the YouTube app. And then he opened the app and started swiping and scrolling, and I was like mind blown. And I mean, for a 2-year-old interacting with an iPad and a super complex app, UX-wise, which has lots of complex UX patterns, that was kind of something for me, because I've been living under a rock for like the past 3 years. And that made me think about today's kids' first interactions with technology versus our first interactions with technology. For me, I guess for most of you, our first interaction with technology was through a terminal. And for me, it was like coding basics. So most of what we could do was just writing code, not much else. So that made me think about the whole kids should learn to code, because that's the future thing that everyone's talking about. And I'm like asking myself, do we really need to teach kids how to code for them to have a better future, like to be technologists or whatever? And personally, I believe that kids should have a choice in whether or not they want to learn to code. And that choice actually, well, I went to an Hour of Code event just to try and learn more about kids and coding and the whole ecosystem. Just to sum up the whole experience, the whole Hour of Code event experience, kids will learn to code in a game-based manner. So that actually implicated that they're gonna lose interest eventually, because the games kind of suck. And that didn't fit their pattern, which is smartphones. I mean, most of the games that they were creating were on computer, on desktop. So who knows what this is? So just to put this in perspective, 6-year-olds today were born in 2010, which is the year the iPhone 4 was released, which some people are still using. So why couldn't we shift the whole kids should learn to code movement to smartphones and to mobile? Well, the answer is quite simple, which is mobile has a really steep learning curve and also a complex setup. I mean, if you want to just show up a hello world on Android, that would like, take you half a day of installing whatever. During that event, I discovered this thing, Scratch, which is an intriguing project by MIT's Media Lab, and which allows you basically to construct a story, a game, anything interactive on screen using blocks, puzzle blocks. So for instance, this quote-unquote app allows the kid to show hello world whenever they click on the flag. But they do this by dragging and dropping blocks, events, controls, and so on, and setting parameters. So these blocks actually could create React native apps. That was like the first question was like, could we use something similar to create mobile apps? And these blocks actually made me think about React components. So I made a little mock-up on Balsamiq 1901. So this was like the first mock-up when I thought about this, and then that implicated I made this app, which is like a super basic prototype. It has like 3 screens, pieces of the puzzles, and then a workspace where the kid can drag and drop components. And whenever they drag and drop components, code gets generated, and they can run it on their phone, which is pretty awesome for like a half-a-day project. And by day, I mean week. By week, I mean 2 months. But later I discovered Exponent.js, which is going to be super awesome for this use case. So in summary, I'm going to refer to this whenever someone tells me coding is the new literacy, because computers are everywhere. I ask them how fuel injection works. which is completely right. I don't know how many people here know how fuel injection works or what does that mean. I mean, it has to do with cars. I really believe that kids should have a choice in learning how to, whether or not they want to code, and React Native using what I showed is a really good start. And that's it. Thank you very much.
All right, that is it. That's everything. So I guess before we go, I want to say thank you to everyone who's behind us here. Probably not many of you have seen that, but there's like 10 people back there and like a lot of equipment and all that to live stream this out to people and record it for later. I don't know if people need to see me in that high definition, but you're going to. I guess you can turn it down. I think YouTube has that option. Yeah, and also, of course, the other organizers. So as I mentioned before, Christina and Mylene really did all the hard work for this. And of course, Paul organizing the diversity scholarship, which was really amazing. So that's great on Paul. So what we're going to do now is, if everyone could just leave as fast as possible, because everyone actually has to be out of this space pretty quick, not even joking. And, yeah, and to further motivate, yeah, well, I don't know if that's legal or whatever, but I would say, if I could just scream, yeah, I'm not going to even say the word. So if we could just orderly, don't trample people, but, you know, leave. And go up the escalators, go to the lobby. Yeah, the lights are on, that means go home, right? But like, go to the lobby. 3 elevators will be going up to the 36th floor, where you can eat food and drink alcoholic or non-alcoholic beverages and listen to Tom Occhino. Cool, thanks.